Tonight, we will discuss the entire history of quantum mechanics. Get ready to question reality itself. Right now, as you watch this documentary, trillions of particles in your body are doing something that should be impossible. They're existing in multiple places at once, spinning in all directions simultaneously, and somehow knowing about particles on the other side of the universe instantly. What if everything you think you know about reality is wrong? What if the solid world around you is actually a shimmering probability cloud, where particles dance between existence and non-existence until the very moment you observe them? Welcome to quantum mechanics, the most successful theory in human history and the most disturbing. This is the story of how humanity discovered that the universe operates on rules so bizarre, so counterintuitive, that even Albert Einstein spent his final years trying to prove them wrong. From ancient Greek philosophers who first dared to ask, "What is everything made of?" to today's quantum computers that threaten to revolutionize civilization itself, this is the complete chronicle of the most revolutionary idea in human thought. Prepare to question everything you believe about reality, because by the end of this journey, you'll never look at the world the same way again. Chapter 1. The First Quantum Dreamers. You're holding a grain of sand. Now imagine cutting it in half, cut it again and again, keep cutting deeper and deeper, smaller and smaller. How long could you continue this process? Is there a point where you simply cannot cut any further? Where you reach something truly indivisible? Or could you keep slicing forever into infinity itself? This question haunted a brilliant philosopher walking the dusty streets of ancient Greece 24 centuries ago. His name was Democritus, and the answer he proposed was so revolutionary, so far ahead of its time, that it would take over 2,000 years for humanity to prove him right. Yet without knowing it, this ancient thinker had just laid the conceptual foundation for quantum mechanics, the theory that would eventually reveal that reality itself is built from indivisible packets of energy, behaving in ways so strange they would make even Democritus's wildest dreams seem tame. Today we take for granted that everything around us, your coffee cup, the air you breathe, even your own body, is made of atoms. But this idea was once so dangerous, so threatening to established ways of thinking, that it nearly vanished from human knowledge entirely. The story of how it survived, evolved, and ultimately gave birth to our modern understanding of the quantum world is a tale of intellectual courage, religious persecution, and scientific resurrection that spans over 2 millennia. In the 5th century before Christ, while most people believed the world was made of 4 simple elements, earth, air, fire, and water, a small group of Greek philosophers dared to imagine something far more radical. Democritus and his teacher Leucippus proposed that if you could somehow cut that grain of sand small enough, you would eventually reach a point where no further division was possible. They called these ultimate, indivisible particles atomos, literally meaning uncuttable in ancient Greek. But Democritus went far beyond just naming these invisible building blocks. He envisioned a universe where countless atoms, too small to see, moved through empty space according to natural laws. Different arrangements and movements of these atoms, he argued, created everything we experience: the hardness of stone, the fluidity of water, the warmth of fire, even the thoughts in our minds. It was a breathtakingly materialist vision. Everything in existence, from the grandest mountain to the most subtle emotion, was nothing more than atoms dancing in the void. Think about how radical this idea truly was. Democritus was essentially saying that there is no fundamental difference between a rock and a human being. Both are simply different arrangements of the same basic ingredients. No gods were required to explain the complexity of nature. No mysterious life forces or spiritual essences, just atoms, void, and the laws governing their motion. It was reductionism taken to its logical extreme, and it pointed toward a mechanistic universe that wouldn't be fully accepted until the scientific revolution over 2,000 years later. What made Democritus's atomic theory even more remarkable was how eerily it anticipated concepts that modern quantum mechanics would later confirm. He proposed that atoms came in different shapes and sizes, that they combined and separated to form different substances, and that they moved randomly through space. He even suggested that our perception of reality, colours, tastes, sounds, existed only in our minds, while the underlying reality consisted of nothing but atoms moving in emptiness. By convention, sweet is sweet, bitter is bitter, hot is hot, cold is cold, colour is colour, he wrote. In truth, there are only atoms and the void. This insight would prove prophetic. Modern quantum mechanics tells us that the properties we observe in objects, their color, their temperature, their texture, emerge from the quantum behavior of subatomic particles that themselves possess none of these familiar characteristics. An electron has no color, no texture, no temperature in the way we understand these concepts, yet somehow collections of these colorless, textureless particles create the rich sensory world we inhabit. But Democritus's atomic vision contained an even deeper anticipation of quantum weirdness. He argued that atoms were indivisible not because they were physically too hard to cut, but because division itself became meaningless at the atomic scale. This prefigured one of quantum mechanics' most startling discoveries, that at the smallest scales, the very concepts of classical physics, exact position, definite momentum, continuous motion, break down entirely. The brilliance of the ancient atomists lay not just in their specific insights, but in their method of thinking. They realized that to understand the complex world we observe, we must imagine an underlying reality that is simpler, more fundamental, and often completely unlike our everyday experience. This approach, looking beneath the surface appearances to find deeper, more universal principles, would become the hallmark of all great physical theories, from Newton's laws to Einstein's relativity to quantum mechanics itself. Yet for all its prescience, Democritus's atomic theory faced a formidable opponent who would nearly erase it from human memory for the next 2 millennia. Aristotle, the most influential philosopher of the ancient world, found the atomic hypothesis deeply troubling and set out to demolish it with all the intellectual firepower at his disposal. Aristotle's rejection of atomic theory wasn't based on experimental evidence. Such evidence wouldn't be available for over 2,000 years. Instead, his opposition stemmed from philosophical principles that seemed, at the time, far more reasonable and intuitive than the atomists' radical materialism. To Aristotle, the idea of atoms moving in empty void was not just wrong, it was literally impossible. How could empty space, which is nothing at all, actually exist? How could motion occur without a medium to move through? In his physics, every movement required a mover, every change needed a cause, and empty space was a logical contradiction. The atomist's vision of particles careening through nothingness struck him as philosophical nonsense. Instead, Aristotle proposed that all space must be filled with matter. There could be no true vacuum anywhere in the universe. Matter, he argued, was infinitely divisible. No matter how small you cut something, you could always cut it smaller still. This seemed far more sensible than the atomist's claim that division must eventually reach a natural limit. But Aristotle's critique went deeper than physics. It touched on the very nature of knowledge itself. The atomists claimed that reality consisted of invisible particles that could never be directly observed, moving according to laws that could only be inferred, never directly experienced. To Aristotle, this was bad philosophy. True knowledge, he insisted, must be based on what we can actually observe and experience. The invisible, hypothetical atoms of Democritus might make for interesting speculation, but they could never form the basis of genuine scientific understanding. This methodological disagreement would echo through the centuries and re-emerge dramatically in quantum mechanics. Many of the theory's early critics, including Einstein himself, would essentially repeat Aristotle's objection. How can we base our understanding of reality on entities and processes we can never directly observe? The quantum world of probability waves, virtual particles, and measurement-dependent reality would strike them as every bit as problematic as Democritus's atoms struck Aristotle. Aristotle's alternative vision proved devastatingly influential. His four-element theory, earth, air, fire, and water, combined with his belief in the impossibility of empty space, dominated Western thought for nearly 2,000 years. The atomic hypothesis didn't just lose the philosophical debate, it was so thoroughly discredited that it virtually disappeared from European intellectual life. Yet there was bitter irony in this victory of Aristotelian physics. While Aristotle's rejection of atoms seemed more reasonable and scientifically rigorous than the speculative materialism of Democritus, it was actually Aristotle's approach that would prove to be the dead end. His insistence on basing knowledge only on direct observation, while admirable in principle, failed to recognize that the deepest truths about nature might be hidden from our immediate senses. The atomic hypothesis, for all its apparent speculative wildness, pointed toward a more powerful way of understanding the world, one that would eventually give birth to modern science itself. The suppression of atomic theory created a scientific dark age that lasted until the Renaissance. But ideas like atoms themselves have a way of surviving even the most hostile environments. While atomic thinking vanished from Christian Europe, it found refuge in a very different intellectual climate, where it would not only survive but flourish in ways that would astonish its original creators. While Christian Europe largely forgot the atomic hypothesis, the Islamic world embraced and developed it with remarkable sophistication. Islamic scholars didn't just preserve Democritus's ideas, they refined them, expanded them, and connected them to new areas of inquiry that would prove crucial for the later development of chemistry and eventually quantum mechanics. The Islamic atomist tradition began in the 9th century with scholars like Al-Jahiz and reached its peak with the brilliant philosopher and physician Al-Ghazali in the 11th century. But it was Islamic alchemists and natural philosophers who made the most startling advances, developing atomic theories that were in some ways more sophisticated than anything Europe would produce until the 17th century. These medieval Islamic thinkers proposed that atoms were not just indivisible particles of matter, but discrete units of space and time as well. They imagined reality as fundamentally granular, made up of indivisible atoms of matter, moving through indivisible atoms of space during indivisible atoms of time. This vision of quantized space and time wouldn't reappear in Western thought until the 20th century, when quantum mechanics and relativity began to suggest that space and time themselves might have atomic structure. Even more remarkably, some Islamic atomists proposed that the properties we observe in objects, their colors, tastes, and textures, are not inherent in the atoms themselves, but emerge only when atoms combine in specific ways. This insight anticipated one of modern chemistry's most important discoveries, that the properties of molecules arise from the arrangement and interaction of their constituent atoms, not from any inherent qualities of the atoms themselves. The Islamic preservation and development of atomic thinking became crucial when these ideas finally returned to Europe during the Renaissance. Through translations of Arabic texts and contact with Islamic scholars in Spain and Sicily, European intellectuals rediscovered the atomic hypothesis after nearly 1,000 years of neglect. But they didn't just recover the ancient Greek version, they inherited a far more sophisticated atomic theory that had been refined by centuries of Islamic scholarship. This medieval resurrection of atomic thinking came with a crucial addition that the ancient Greeks had lacked: a practical experimental tradition. Islamic alchemists didn't just speculate about invisible particles. They manipulated matter in their laboratories, transforming substances, purifying metals, and creating new compounds. While their theoretical framework was still centuries away from modern chemistry, their hands-on approach to understanding matter pointed toward the experimental method that would eventually make atomic theory scientifically testable. The alchemical tradition, despite its mystical elements and impossible goals like transmuting base metals into gold, actually laid essential groundwork for quantum chemistry. Alchemists developed sophisticated ideas about the relationships between different substances, the role of heat and light in chemical transformations, and the hidden properties that determine how different materials behave. They were, without knowing it, probing the quantum mechanical forces that hold atoms together and drive chemical reactions. Perhaps most importantly, the medieval resurrection of atomic thinking preserved the essential insight that had made Democritus's theory so powerful: the recognition that visible reality emerges from an invisible underlying structure. This principle, that what we observe is the surface manifestation of deeper, hidden processes, would become the cornerstone of all modern physics, from Newton's gravitational forces to Maxwell's electromagnetic fields to the quantum wave functions that govern atomic behavior. As European scholars absorbed these recovered atomic ideas during the Renaissance and scientific revolution, they began to develop new mathematical and experimental tools that would eventually make it possible to test atomic theories directly. But even before that empirical confirmation became possible, a new generation of natural philosophers began to explore another puzzle that would prove intimately connected to the atomic structure of matter: the mysterious nature of light itself. In 17th century England, as the scientific revolution gained momentum, natural philosophers began encountering phenomena that would plant the first seeds of quantum mechanics. They didn't know it at the time, but their investigations into the nature of light were uncovering clues about the fundamental graininess of energy itself, the same graininess that Democritus had proposed for matter 20 centuries earlier. Robert Hooke, examining thin films of soap bubbles and oil slicks under his microscope, noticed something puzzling. These films displayed brilliant colours that shifted and changed as he moved them, creating rainbow patterns that seemed to have nothing to do with the materials themselves. The colours, he realized, must be related to the thickness of the films and somehow connected to the nature of light itself. His careful observations revealed that light behaved in ways that suggested an underlying structure, as if light itself might be made of discrete units, like atoms of illumination. Hooke's insights led him to propose that light consisted of rapid vibrations or pulses travelling through space. This was a revolutionary idea because it suggested that light, like matter, might have atomic characteristics, that it might come in discrete packets rather than flowing continuously like a river. He couldn't have known that he was anticipating one of quantum mechanics' most startling discoveries, that light indeed comes in indivisible units called photons, each carrying a specific quantum of energy. But Hooke's pulse theory of light immediately ran into competition from the towering figure of Isaac Newton, who proposed an entirely different model. Newton argued that light consisted of tiny particles, corpuscles, that travelled through space like microscopic bullets. This particle theory seemed to explain many optical phenomena more elegantly than Hooke's wave theory, and Newton's prestige gave it enormous influence. Yet even as Newton championed the particle nature of light, he encountered phenomena that his theory couldn't easily explain. When he passed white light through a prism and split it into rainbow colours, he discovered that different colours bent by different amounts. This suggested that different colours of light had different properties, as if white light were actually a mixture of distinct types of illumination, each with its own characteristics. Newton's prism experiments revealed something profound about the relationship between light and matter. When light interacted with materials, passing through glass, reflecting from metals, or being absorbed by pigments, it did so in ways that seemed to depend on hidden properties of both the light and the material. It was as if light and matter were engaged in a subtle dance governed by rules that remained invisible to 17th century investigators. Meanwhile, on the continent, the Dutch physicist Christiaan Huygens was developing a wave theory of light that directly challenged Newton's particle model. Huygens argued that light propagated as waves spreading through an invisible medium, much like ripples spreading across a pond. His wave theory could explain optical phenomena that puzzled Newton's particle theory, particularly the way light bent when passing from one material to another. This disagreement between Newton and Huygens established the first great wave-particle debate in physics, a controversy that would remain unresolved for over 2 centuries until quantum mechanics revealed that light is simultaneously both wave and particle, depending on how we choose to observe it. The 17th century debate was, without anyone realizing it, the first glimpse of quantum mechanical complementarity, the principle that quantum objects can exhibit mutually exclusive properties depending on the experimental context. The deeper significance of these early optical investigations lay not in their specific conclusions, but in what they revealed about the relationship between observation and reality. Both Newton and Huygens realized that the nature of light could only be inferred from its interactions with matter, from the way it reflected, refracted, and interfered. They were discovering, centuries before quantum mechanics made it explicit, that we can never observe light itself directly. We can only observe the effects it produces when it encounters matter. This insight would prove prophetic. Quantum mechanics would eventually reveal that all our knowledge of the microscopic world comes through similar indirect inferences. We never observe electrons or photons or atoms directly, only the traces they leave in our measuring instruments. The 17th century wave-particle debate was humanity's first encounter with the fundamental epistemological challenge that would define quantum physics. How can we understand a reality that we can never directly observe? As the 18th century approached, natural philosophers had established the essential conceptual framework that would eventually give birth to quantum mechanics. They had revived the atomic hypothesis and begun to suspect that light, like matter, might have discrete, particle-like properties. They had discovered that the properties we observe in both matter and light emerge from invisible underlying structures, and they had begun to grapple with the puzzling relationship between the continuous world of everyday experience and the apparently granular nature of the microscopic realm. None of these early investigators could have imagined where their insights would lead. They were simply trying to understand how soap bubbles create colours and why prisms split white light into rainbows. But in pursuing these seemingly simple questions, they were unknowingly laying the conceptual groundwork for humanity's strangest and most successful theory. A theory that would reveal that reality itself is far more mysterious, far more beautiful, and far more fundamentally quantum than any of them dared to dream. As the 19th century dawned, scientists felt confident they had solved the great mysteries of matter and energy. Classical physics seemed complete, elegant, and powerful enough to explain everything from planetary motion to the propagation of light. They had no idea that they were about to discover phenomena so puzzling, so completely inexplicable within their classical framework, that they would be forced to abandon their most basic assumptions about the nature of reality itself. The stage was set for the greatest revolution in human thought since Copernicus. The discovery that the universe operates according to quantum rules, so strange that even their discoverers would spend decades trying to convince themselves they couldn't possibly be true. The atomic dreamers of antiquity and the optical pioneers of the scientific revolution had established something remarkable. A vision of reality built from invisible, indivisible units, atoms of matter dancing in the void, packets of light carrying energy through space. Their insights suggested that beneath the continuous, predictable world of everyday experience lay a hidden realm where different rules might apply. But as the 19th century unfolded, this vision seemed increasingly vindicated by classical physics. Scientists had developed mathematical tools powerful enough to predict the motion of planets, the flow of heat, and the propagation of electromagnetic waves with extraordinary precision. The atomic hypothesis was gradually gaining acceptance, but it was being absorbed into a thoroughly classical worldview where atoms behaved like tiny billiard balls governed by Newton's laws of motion. Everything seemed to fit together beautifully. Matter was made of atoms, energy flowed continuously, and the universe operated like a vast, precise machine. Scientists were so confident in this classical picture that some began to proclaim the end of physics itself. All the fundamental principles had been discovered, they claimed, and only minor details remained to be worked out. They had no idea how wrong they were. Hidden in those minor details were observations so disturbing, so completely incompatible with classical physics, that they would shatter humanity's understanding of reality itself. The black-body radiation that should have been a simple application of known principles would instead reveal that energy comes in discrete packets. The photoelectric effect that seemed like a straightforward problem in optics would prove that light behaves like particles. The spectral lines emitted by atoms would show that matter itself operates according to quantum rules. As the 19th century drew to a close, scientists were about to discover that Democritus's ancient dream of an atomic reality was not just true, it was far stranger than even he had imagined. The atoms were there, but they didn't behave like anything in the classical world. And the energy that flowed between them came not in smooth streams, but in discrete, indivisible quanta that would give their name to the most revolutionary theory in human history. The cracks in classical reality were about to become chasms, and through those chasms, humanity would glimpse a quantum universe so bizarre that it would challenge our most basic notions of what it means for something to exist. Chapter 2. The cracks in classical reality. Imagine you're standing in a pristine Victorian laboratory in 1890, surrounded by brass instruments gleaming like jewellery, their polished surfaces reflecting gaslight. The air thrums with confidence. Scientists believe they've nearly solved the puzzle of the universe. Matter is made of atoms, energy follows predictable laws, and light behaves exactly as waves should. Physics, they declare, is essentially complete. All that remains is measuring constants to a few more decimal places. But hidden in the shadows of this triumph lurk four seemingly innocent problems. Problems so simple a child could state them, yet so profound they would topple everything these confident Victorians believed about reality itself. Let me tell you about the problem that started it all. A puzzle so mundane it might bore you to tears, until you realize it threatened to destroy all of physics. Imagine you're a blacksmith, hammering red-hot iron. As the metal heats up, it glows brighter and changes color, first deep red, then orange, then yellow, and if you could heat it hot enough, brilliant white. This simple observation had puzzled scientists for decades. Why does hot metal change color in such a predictable way? The question seemed straightforward enough that by the 1890s, physicists thought they had it solved. They called these perfectly absorbing, perfectly emitting objects black bodies. Not because they're black, but because they absorb all colors of light that hit them. Every star in the sky is essentially a black body. So is the filament in an old-fashioned light bulb. Even you are a black body glowing invisibly in infrared light at your body temperature of 98.6 degrees Fahrenheit. Classical physics provided what seemed like a bulletproof explanation. Inside any hot object, electromagnetic waves bounce around like sound waves in a concert hall. The hotter the object, the more energetic these waves become, and the shorter their wavelengths, which is why hot things glow blue-white while cooler things glow red. But when physicists tried to calculate exactly how much energy a black body should emit at each wavelength, their mathematics led them into a nightmare. According to classical physics, a hot object should emit infinite amounts of ultraviolet radiation. Not just a lot, infinite. Every hot cup of coffee should instantly incinerate everything around it with invisible death rays. Every star should explode in an instant burst of unlimited energy. This wasn't just wrong, it was catastrophically, absurdly wrong. Scientists called it the ultraviolet catastrophe, though catastrophe hardly captures the magnitude of the failure. Classical physics had predicted that reality itself was impossible. By 1900, this seemingly innocent problem about glowing metal had become physics's most embarrassing secret. The very foundation of thermal physics, the science that powered the Industrial Revolution, rested on mathematics that said the universe should have destroyed itself the moment the first star ignited. Something was fundamentally broken in humanity's understanding of energy and matter. But what? While the blackbody problem simmered in laboratories across Germany, another puzzle was emerging from an entirely different corner of physics, one that would ultimately hand a young patent clerk named Albert Einstein his Nobel Prize, and overturn our understanding of light itself. The photoelectric effect sounds like the most boring phenomenon imaginable. Shine light on certain metals, and they emit electrons. That's it. You've probably seen this effect in action every time you use an automatic door sensor or a solar panel. Light goes in, electrons come out. What could be simpler? But when physicists in the 1880s began studying this effect carefully, They discovered something that made absolutely no sense according to classical physics. Picture light as a wave, which is exactly how 19th century physicists understood it. Waves carry energy, and the brighter the light, the bigger the wave, the more energy it should deliver. So when you shine bright light on a metal surface, the electrons should come flying out with tremendous energy. Dim the light, and the electrons should emerge more slowly. Instead, experiments revealed something utterly baffling. The energy of the emitted electrons depended not on the brightness of the light, but on its color. Bright red light couldn't knock out a single electron from certain metals, no matter how intense you made it, but even dim blue light could send electrons streaming out immediately. Even stranger, there was no delay. Classical wave theory predicted that dim light should gradually build up energy on the metal surface until electrons finally gained enough energy to escape. Instead, even the faintest blue light produced electrons instantly, as if the light was delivering its energy in discrete packets rather than as a continuous wave. This made no sense whatsoever. It was like discovering that a gentle pat from a heavy person couldn't budge a door, but the lightest touch from a child could swing it wide open instantly. For 20 years, the photoelectric effect remained physics' most embarrassing mystery. Classical wave theory, which had successfully explained every other property of light, failed completely to explain this simple phenomenon. The mathematics that described how waves behave simply couldn't account for what was happening when light hit metal. The failure was so complete, so fundamental, that it suggested something revolutionary. Maybe light wasn't a wave at all. As if the black-body catastrophe and photoelectric heresy weren't enough to shake physicists' confidence, the 1880s delivered a third blow to classical physics, one that emerged from the most beautiful discovery in all of science. Joseph von Fraunhofer was a young German glassmaker with an insatiable curiosity about light. In 1814, he built the finest prism spectrometer anyone had ever seen and pointed it at the sun. What he saw changed our understanding of the cosmos forever. Sunlight, when passed through a prism, doesn't just split into a rainbow. It splits into a rainbow crossed by hundreds of dark lines, as if someone had drawn thin black pen marks across the spectrum. These lines appeared at precisely the same wavelengths every time Fraunhofer looked. They weren't random. They formed patterns as precise and reproducible as musical notes. By the 1860s, scientists had discovered that every element in the periodic table produces its own unique pattern of spectral lines when heated to incandescence. Hydrogen produces a series of lines in the red, blue, green and violet regions of the spectrum. Sodium produces two bright yellow lines so characteristic that you can identify sodium instantly just by its light. Iron produces hundreds of lines scattered across the entire spectrum like a complex barcode. This discovery revolutionized astronomy overnight. By analyzing the light from stars, scientists could determine exactly which elements they contained, even though those stars were trillions of miles away. They could measure stellar temperatures, compositions and motions with unprecedented precision. Spectroscopy became astronomy's most powerful tool. But there was a problem that kept physicists awake at night. Nobody had the faintest idea why atoms produced these specific patterns of light. Classical physics suggested that electrons inside atoms should be able to vibrate at any frequency, just like a violin string can be plucked to produce any note. If this were true, atoms should emit light at all wavelengths, a continuous rainbow rather than discrete lines. Instead, atoms behaved like musical instruments that could only play specific, predetermined notes. Hydrogen atoms always emitted red light at exactly 656.3 nanometers, blue-green light at exactly 486.1 nanometers, and violet light at exactly 434.0 nanometers, never anything in between. In 1885, a Swiss high school teacher named Johann Balmer discovered something even more mysterious. The wavelengths of hydrogen's spectral lines followed a simple mathematical formula. They were related to the squares of integers. The red line corresponded to the difference between 1/4 and 1/9. The blue-green line to the difference between 1/4 and 1/16. The violet line to the difference between 1/4 and 1/25. Why should atoms care about the squares of integers? Why should light emission follow such precise mathematical rules? Classical physics offered no explanation whatsoever. It was as if atoms contained hidden mathematical machinery that determined exactly which colours of light they could emit. The spectral lines were beautiful, precise, and utterly incomprehensible according to 19th century physics. They suggested that atoms had internal structure governed by laws nobody understood. Just as physicists were grappling with mysterious spectral lines and impossible photoelectric effects, Marie and Pierre Curie were about to deliver the most shocking blow of all to classical certainty. In 1896, Henri Becquerel made an accidental discovery that would forever change our understanding of matter itself. He had left some uranium salts in a drawer with a photographic plate, separated only by black paper. When he developed the plate later, he found it had been exposed, as if the uranium was emitting invisible radiation right through the paper. This was already strange enough, but when Marie Curie began studying this phenomenon for her doctoral thesis, she discovered something even more unsettling. The intensity of radiation from uranium samples depended only on the amount of uranium present, not on its chemical form, not on its temperature, not on any external conditions whatsoever. This violated everything 19th century chemistry had taught about matter. Chemical properties were supposed to depend on how atoms combined with other atoms, but radioactivity seemed to be an intrinsic property of certain atoms themselves, completely independent of their chemical environment. Working with her husband Pierre in a freezing shed that served as their laboratory, Marie Curie processed tons of uranium ore by hand, stirring huge vats of boiling radioactive sludge with an iron rod nearly as tall as herself. She was searching for the source of radiation more intense than pure uranium could account for. After 4 years of backbreaking work, she isolated 1/10 of a gram of a new element she named radium, an element so radioactive it glowed in the dark and was warm to the touch. But radium presented physicists with an impossible puzzle. Here was an element that produced energy continuously, apparently from nothing. Radium salts glowed, emitted heat, and produced mysterious rays strong enough to penetrate solid matter, all without any external energy source. Where was this energy coming from? According to the law of conservation of energy, the most fundamental principle in physics, energy cannot be created or destroyed. Yet radium seemed to violate this law every second of every day, producing energy from thin air. Even more disturbing was radium's behavior over time. Marie Curie discovered that radioactive materials decayed at absolutely predictable rates, but the decay of individual atoms was completely random. Half of any radium sample would decay in 1,600 years, as predictable as clockwork, but which specific atoms would decay in any given second was utterly unpredictable. This randomness struck at the heart of scientific determinism. Since Newton, physicists had believed that if you knew the position and velocity of every particle in the universe, You could predict the future with perfect accuracy. The universe was a vast clockwork machine, precise and predictable. Radioactivity suggested otherwise. Here was a phenomenon that was simultaneously perfectly predictable in bulk and completely random in detail. Classical physics, which had no room for true randomness, could not explain how nature could be both deterministic and random at the same time. Then, in 1909, Ernest Rutherford delivered the final blow to classical atomic theory. He fired alpha particles, helium nuclei, at a thin sheet of gold foil, expecting them to pass through with only slight deflections. After all, if atoms were the solid, indivisible building blocks of matter that scientists imagined, alpha particles should barely be affected by such a thin barrier. Instead, Rutherford observed something that shook him to his core. Most alpha particles passed through the gold foil undeflected, as expected, but a tiny fraction bounced straight back, as if they had hit something incredibly dense and small. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper, and it came back and hit you, Rutherford later recalled. The only way to explain these results was revolutionary. Atoms were not solid spheres, but mostly empty space, with all their mass concentrated in an incredibly tiny, dense nucleus at the center. The electrons somehow orbited this nucleus like planets around the sun, but the nucleus itself was 10,000 times smaller than the atom as a whole. This discovery meant that everything around you, your body, the chair you're sitting in, the building that shelters you, is almost entirely empty space. The apparent solidity of matter is an illusion created by electromagnetic forces between particles separated by vast gulfs of nothingness. But Rutherford's nuclear model created an immediate crisis. According to classical physics, orbiting electrons should continuously emit electromagnetic radiation, losing energy and spiraling into the nucleus in a fraction of a second. Every atom in the universe should collapse instantly. The fact that you exist to hear these words proves that classical physics was fundamentally wrong about the nature of matter itself. By 1900, 4 seemingly simple questions had shattered the confident edifice of classical physics. Why do hot objects glow the colors they do? Why does light knock electrons out of metals in such a strange way? Why do atoms emit light only at specific wavelengths? Why do some atoms spontaneously emit energy and transform into other elements? These weren't minor puzzles that required small adjustments to existing theory. They were fundamental contradictions that struck at the heart of everything physicists thought they knew about energy, matter, and light. The 19th century had ended with physics in crisis. Classical mechanics, electromagnetic theory, and thermodynamics, the 3 pillars of 19th century physics, all failed to explain these basic phenomena. Something was deeply, fundamentally wrong with humanity's understanding of nature. But crises in science often herald revolutions. In Berlin, a conservative physicist named Max Planck was about to make a desperate mathematical guess that would change everything. He had no idea that his reluctant solution to the blackbody problem would unleash a scientific revolution more profound than anything in human history. The quantum age was about to begin, and with it our entire conception of reality was about to be turned upside down. Chapter 3. The Reluctant Revolutionary. It's December 14th, 1900, in Berlin. A middle-aged physics professor stands before the German Physical Society, about to announce a mathematical formula that will destroy everything scientists believe about reality. His name is Max Planck, and he's terrified of what he's about to say, not because it's wrong, but because it might be right. What Planck doesn't know, as he clears his throat and begins to speak, is that he's about to give birth to quantum mechanics. The word quantum doesn't even exist yet. Neither does the concept. All Planck knows is that he's found a mathematical trick that solves an impossible problem, and this trick involves an assumption so bizarre, so contrary to common sense, that he'll spend the next 20 years of his life trying to prove it wrong. This is the story of how the quantum age began not with a revolutionary battle cry, but with a conservative physicist's reluctant whisper. To understand Max Planck's revolutionary moment, we need to travel back to one of the most embarrassing problems in the history of physics. Scientists called it the black-body radiation problem, but they might as well have called it the mystery that makes no sense. Here's the puzzle that was driving physicists to despair. When you heat up any object, a piece of metal, a rock, even your own body, it glows. The hotter it gets, the brighter it glows, and the colour changes from red to orange to white to blue. This much everyone knew. But when physicists tried to calculate exactly how much light should come from a hot object using their best theories, they got an answer that was not just wrong, it was catastrophically, absurdly wrong. According to classical physics, every hot object should emit infinite amounts of ultraviolet light. Not just a lot, infinite. If this were true, a simple campfire would instantly incinerate everything within miles, and every warm object in the universe would be pumping out deadly radiation. Scientists called this the ultraviolet catastrophe, and it represented nothing less than the complete failure of classical physics to explain one of the most basic phenomena in nature. Max Planck had been wrestling with this problem for 6 years. 6 long years of mathematical dead ends and theoretical frustration. He was 52 years old, a respected but not particularly revolutionary physicist who believed deeply in the power of classical physics to explain everything. The blackbody problem was supposed to be his triumph, the crowning achievement that would cement his reputation. Instead, it had become his obsession and his torment. Then, in a moment of what he would later call desperation, Planck made a guess. It wasn't based on any deep physical insight or revolutionary new understanding of nature. It was pure mathematical intuition, a wild stab in the dark. What if, Planck wondered, energy doesn't flow smoothly and continuously as everyone assumed? What if energy comes in tiny, discrete packets, like coins in a wallet rather than water from a faucet? The idea seemed ridiculous. Everyone knew that energy was continuous. You could have any amount of energy you wanted. Half a joule, 1 3/4 joules, pi joules. Energy was like a dimmer switch that could be set to any level. But Planck's mathematical intuition whispered a different possibility. What if energy was more like a staircase, where you could only stand on specific steps, never between them? So Planck made his desperate gambit. He assumed that the energy carried by light waves could only come in specific discrete amounts, multiples of some fundamental unit. He called these packets quanta, from the Latin word for how much, and when he plugged this strange assumption into his equations, something miraculous happened. The infinite catastrophe disappeared. The mathematics suddenly worked perfectly, matching experimental observations with stunning precision. But Planck stared at his equations with growing horror. His mathematical trick had worked too well. It wasn't just a convenient approximation, it seemed to be telling him something fundamental about the nature of reality itself. Energy, according to his formula, really did come in discrete packets. The smooth, continuous flow of energy that every physicist took for granted was an illusion. As 1900 drew to a close, Max Planck had solved the blackbody problem, but he had opened a door to a reality far stranger than anyone had imagined. and the man who opened that door would spend decades trying desperately to close it again. Hidden within Planck's equation was a number so small it defied imagination, yet so important it would govern every quantum phenomenon in the universe. Today, we call it Planck's constant, and its value is approximately 6.626 times 10 to the negative 34th power joule seconds. To put this in perspective, if you wrote out this number in decimal form, you would need to write 33 zeros after the decimal point before you got to the first significant digit. This number seems ridiculously, almost insultingly small. Why should such a tiny quantity matter to anything in the real world? The answer reveals one of the most profound insights in all of physics. Planck's constant is the reason our everyday world appears classical and predictable, while the microscopic world operates by the bizarre rules of quantum mechanics. Think of Planck's constant as nature's fundamental unit of action, the smallest possible coin in the universe's energy exchange. Just as you can't pay for something with half a penny because half a penny doesn't exist, quantum systems cannot exchange energy in amounts smaller than multiples of Planck's constant. This quantum graininess is always there, underlying everything, but it's usually so fine that we never notice it. Imagine trying to build a sandcastle on a beach, where each grain of sand was the size of a basketball. Every scoop of your bucket would contain just a few enormous grains, and your sandcastle would look lumpy and discontinuous. That's what the quantum world is like, chunky and grainy at the smallest scales. But now imagine building the same sandcastle with ordinary sand, where each grain is microscopic. With millions of tiny grains in each scoop, your sandcastle appears smooth and continuous. That's our everyday world. Quantum effects are there, but the grains are so incredibly small that everything appears smooth and classical. This is why you don't notice quantum effects when you drive your car or throw a baseball. The energies involved are so large compared to Planck's constant that the quantum graininess becomes invisible. A baseball contains roughly 10 to the 25th power particles, each one obeying quantum rules, but collectively they behave so classically that Newton's laws work perfectly for predicting where the ball will land. But shrink down to the level of individual atoms and molecules, and Planck's constant becomes the most important number in physics. Suddenly the quantum graininess matters enormously. Electrons can only orbit atomic nuclei at specific energy levels, separated by amounts determined by Planck's constant. Light can only be absorbed or emitted in specific packets, with energies that are multiples of Planck's constant times the light's frequency. The entire periodic table, the stability of matter, the colours of flowers, the warmth of sunlight, all of it emerges from the fundamental quantum graininess encoded in that impossibly small number Max Planck discovered in his moment of desperation. What makes this even more remarkable is that Planck's constant isn't just important for obscure quantum phenomena. It sets the scale for all of reality. It determines the size of atoms, the brightness of stars, the rate of radioactive decay, and even the fundamental limits of what we can know about the universe. In many ways, Planck's constant is nature's signature, written into the fabric of reality itself. Yet the man who discovered this cosmic constant would never fully appreciate its revolutionary implications. To Planck, it remained an unfortunate mathematical necessity, a regrettable departure from the smooth, predictable world of classical physics that he loved so dearly. Here's one of history's greatest ironies. The man who started the quantum revolution spent the rest of his life trying to stop it. Max Planck, the reluctant father of quantum mechanics, never truly believed in his own discovery. For more than 2 decades after his groundbreaking 1900 paper, he searched desperately for a way to return energy to its classical, continuous nature. Understanding Planck's resistance requires understanding the man himself. Born in 1858 into a family of scholars and judges, Planck embodied the German intellectual tradition of careful, methodical thinking. He was deeply conservative by nature, suspicious of revolutionary ideas, and committed to the belief that physics should reveal an orderly, rational universe governed by deterministic laws. The idea that nature might be fundamentally discontinuous and probabilistic struck him as not just wrong, but almost morally offensive. So even as other physicists began to embrace and extend his quantum ideas, Planck embarked on what we might call his Great Retreat. He tried every mathematical approach he could imagine to derive his successful black-body formula without assuming that energy came in discrete packets. He explored whether quantum effects might emerge from some deeper classical theory. He wondered whether his energy quanta were just a convenient fiction, a mathematical trick with no physical reality. Year after year, Planck published papers attempting to restore classical continuity to physics. He developed increasingly elaborate theories to explain how apparently discrete energy packets might arise from truly continuous processes. He was like a man who had accidentally invented the airplane while trying to build a better horse-drawn carriage, and who spent years trying to convince everyone that flight was impossible. But the universe refused to cooperate with Planck's conservative instincts. Every new experiment confirmed the reality of energy quantization. Einstein used Planck's quantum idea to explain the photoelectric effect. Bohr applied it to atomic structure. The quantum concept kept proving itself more and more essential to understanding nature, no matter how much its discoverer wished it would go away. What makes Planck's story even more poignant is that he was an extraordinarily gifted physicist. His attempts to avoid quantum mechanics led him to insights that were brilliant, creative, and ultimately futile. He understood the mathematics of his own discovery better than almost anyone, which made his inability to accept its implications all the more tragic. He could see exactly where quantum mechanics led, and he desperately didn't want to go there. The turning point came gradually through the 1910s and early 1920s. As more and more phenomena required quantum explanations, as younger physicists built increasingly successful theories on quantum foundations, Planck slowly, reluctantly, began to accept what he had unleashed. It was like watching a master architect come to terms with the fact that his experimental blueprint had become the foundation for an entire city he never intended to build. By the time Planck won the Nobel Prize in 1918 for his quantum theory, he had largely made peace with his revolutionary discovery, but he never stopped being amazed by it. In his later years, he would often reflect on the strange twist of fate that had made him, of all people, the father of quantum mechanics. He remained convinced until his death in 1947 that some deeper, more classical understanding of nature would eventually emerge. Planck never lived to see that vindication. Instead, he witnessed quantum mechanics grow into the most successful theory in the history of science, explaining everything from the structure of atoms to the behavior of semiconductors to the nuclear reactions that power the sun. The reluctant revolutionary had started something that would transform not just physics, but all of human civilization. As we stand today in our quantum-enabled world, surrounded by laser printers and computer chips and MRI machines, all of which depend on quantum effects, we owe it all to a conservative German professor who made one desperate mathematical guess on a cold December evening in 1900, and who spent the rest of his life marvelling at where that guess had led him. But Planck's story was just the beginning. While he was still trying to put the quantum genie back in its bottle, a young patent clerk in Switzerland was about to grab that genie and set it completely free. Albert Einstein had been paying close attention to Planck's work, and unlike Planck himself, Einstein was ready to take quantum ideas to their revolutionary conclusion. The stage was set for the next great leap into the quantum unknown. As Max Planck reluctantly accepted his role as the father of quantum mechanics, the ideas he had unleashed were about to find their most brilliant and fearless champion. A young man who would take Planck's quantum concept and use it to revolutionize our understanding of light itself was already hard at work in the Swiss Patent Office, dreaming of riding alongside light beams and wondering what secrets the universe might reveal to someone bold enough to ask the right questions. Chapter 4. Einstein's Quantum Awakening. It's 1905, and a 26-year-old patent clerk in Bern, Switzerland, is sitting at his desk examining applications for electrical devices. His name is Albert Einstein, and while the world sees him as a minor government employee who couldn't even land a university teaching job, he's about to publish 4 papers that will shatter humanity's understanding of space, time, matter, and energy forever. But here's what most people don't know about Einstein's miracle year. The paper that would make him most famous wasn't about relativity. It was about light itself, and it would prove that Max Planck's desperate mathematical trick wasn't just a clever calculation. It was a fundamental truth about reality that would launch the quantum revolution into overdrive. You see, Einstein was about to prove that light, the very thing that illuminates our world, comes in tiny, indivisible packets. He was about to show that the wave nature of light that scientists had accepted for over a century was only half the story. And in doing so, he would create a paradox so profound that it would haunt him for the rest of his life. Let me tell you about one of history's greatest ironies. While Einstein was working his day job evaluating patents for electromagnetic devices, he was simultaneously revolutionizing our understanding of electromagnetism itself. The Swiss Patent Office in Bern wasn't exactly the center of the scientific universe, but it gave Einstein something precious: time to think. The year 1905 became known as Einstein's Annus Mirabilis, his miracle year. In the span of just a few months, this unknown patent clerk published 4 papers that would reshape physics forever. There was the paper on Brownian motion that proved atoms were real. There was the special theory of relativity that showed space and time were interwoven. There was the mass-energy equivalence paper that gave us E equals mc squared. But the paper that earned Einstein the Nobel Prize, and the one that launched the quantum revolution beyond anything Planck had imagined, was about something seemingly simple: why certain metals emit electrons when light shines on them. This was called the photoelectric effect, and it was driving physicists absolutely mad. According to everything they knew about light and energy, bright light should knock electrons out of metal more energetically than dim light. Instead, they found something bizarre. The color of the light mattered more than its brightness. Blue light could knock electrons out of zinc with tremendous energy, but no amount of red light, no matter how intense, could budge a single electron. Classical physics had no explanation for this. It was as if you could demolish a brick wall by tapping it gently with a blue hammer, but hitting it with a massive red sledgehammer wouldn't even chip the paint. The effect defied every intuition about how energy worked. Einstein looked at this puzzle and saw something everyone else had missed. He realized that Planck's quantum hypothesis wasn't just a mathematical convenience. It was revealing something fundamental about the nature of light itself. For over a century, scientists had been absolutely certain about light's nature. Thomas Young's double-slit experiment in 1801 had seemed to settle the question once and for all. Light was definitely a wave. You could see it interfere with itself, creating those beautiful patterns of bright and dark bands that only waves could produce. Light bent around corners, it diffracted through small openings, it exhibited every behavior that waves should exhibit. But Einstein proposed something that sounded almost heretical. What if light also behaved like particles? He suggested that light energy comes in discrete packets, little bundles of energy that he would later call photons. Each photon carries a specific amount of energy determined by Planck's constant multiplied by the light's frequency. High-frequency blue light photons pack more energy than low-frequency red light photons, regardless of how many of them there are. This explained the photoelectric effect perfectly. When a blue photon hits an electron in the metal, it delivers enough energy in one concentrated punch to knock the electron free. Red photons, no matter how many of them you send, each carry too little energy individually to do the job. It's like trying to break down a door. One powerful kick might do it, but 1,000 gentle taps won't, no matter how many people are doing the tapping. But here's where things get truly strange. Einstein wasn't saying that light was particles instead of waves. He was saying it was both, simultaneously. This created what scientists call wave-particle duality, and it was the first hint that quantum mechanics would force us to abandon our comfortable either-or way of thinking about reality. Imagine trying to explain this to someone in 1905. Well, you see, light is made of waves that behave like particles, or maybe particles that behave like waves, and somehow it's both at the same time, depending on how you look at it. People thought Einstein had lost his mind. The scientific community was split. Some embraced Einstein's photon theory because it explained experimental results that wave theory couldn't touch. Others rejected it because it seemed to contradict a century of evidence for light's wave nature. This wasn't just a scientific disagreement, it was a fundamental crisis about the nature of reality itself. Here's one of the most fascinating paradoxes in the history of science. Albert Einstein, the man who gave birth to the photon and helped create quantum mechanics, spent the last 30 years of his life trying to destroy his own creation. As quantum mechanics developed through the 1920s, Einstein watched with growing horror as his colleagues embraced interpretations that seemed to make reality itself uncertain and observer-dependent. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, suggested that quantum systems don't have definite properties until they're measured. Particles could exist in multiple states simultaneously, and the act of observation somehow caused reality to crystallize into one specific outcome. Einstein found this deeply disturbing. His famous declaration that God does not play dice with the universe wasn't just a cute quote. It was the anguished cry of a physicist who believed that reality must be deterministic and objective, existing independently of whether anyone observes it. He began devising ingenious thought experiments to expose what he saw as fatal flaws in quantum mechanics. The most famous was the EPR paradox, developed with colleagues Boris Podolsky and Nathan Rosen. They imagined pairs of particles created together, then separated by vast distances. If quantum mechanics was correct, measuring one particle should instantly affect its partner, no matter how far apart they were. Einstein called this spooky action at a distance and argued it proved quantum mechanics was incomplete. Einstein was convinced there must be hidden variables, deeper deterministic laws that quantum mechanics hadn't yet discovered. He spent decades searching for a theory that would restore certainty and locality to physics, that would show quantum uncertainty was just a temporary limitation of human knowledge rather than a fundamental feature of reality. But Einstein's rebellion went even deeper than scientific disagreement. He was troubled by the philosophical implications of quantum mechanics. If reality truly was uncertain and observer-dependent, what did that mean for the nature of existence itself? How could we have objective science if reality depended on the act of observation? The irony is profound. The man who helped birth quantum mechanics became its most eloquent critic. Einstein's photon paper had opened the door to a quantum world, but when he saw what lay beyond that door, he spent the rest of his life trying to close it again. Einstein died in 1955, still believing that quantum mechanics must be wrong or incomplete. He never lived to see John Bell's theorem in 1964, which would prove that Einstein's hidden variables couldn't exist, or Alain Aspect's 1982 experiments that would confirm the reality of quantum entanglement. History would prove that Einstein's quantum intuitions were correct, even when his classical instincts rebelled against them. Einstein had unleashed forces he couldn't control. His photon had proven that light could behave like particles, but this was just the beginning of quantum strangeness. If light exhibited wave-particle duality, what about matter itself? Could atoms and electrons also behave like waves? This question was about to lead a young French physicist named Louis de Broglie to a proposal so audacious it would seem like pure fantasy, until experiments proved it was the deepest truth about matter ever discovered. The quantum revolution was about to take its next impossible leap, one that would show that everything in the universe, including you and me, has a wave nature hidden within its particle appearance. But first, the scientific world needed to grapple with the implications of Einstein's quantum awakening. Light was both wave and particle, which meant our most basic assumptions about the nature of reality were wrong. If something as fundamental as light defied our either-or categories, what else about the universe had we misunderstood? The answer would come from an unlikely source, a Danish physicist studying the structure of atoms, who was about to discover that matter itself obeyed quantum rules that made no sense according to classical physics. Niels Bohr was about to show that atoms themselves were quantum mechanical systems, and in doing so he would open up an entirely new frontier in humanity's understanding of the building blocks of reality itself. Chapter 5. The Atomic Theatre. You're holding a penny in your hand. That small copper disc contains roughly 30 billion trillion atoms. Each one of those atoms should, according to everything scientists understood in 1910, collapse in on itself in less than a trillionth of a second. The electrons orbiting each atomic nucleus should spiral inward like water going down a drain, radiating away their energy until they crash into the nucleus and annihilate the atom entirely. By all rights, that penny, and you and everything in the universe, should have ceased to exist before you could even blink. Yet here you are, and here it is. The fact that atoms exist at all presented early 20th century physics with what seemed like an impossible paradox. The solution to this paradox would not only save the atom from theoretical destruction, it would launch quantum mechanics into a realm so strange that even today, more than a century later, we're still grappling with its implications. To understand how desperate the situation had become, we need to travel back to 1909 to a basement laboratory at Manchester University in England. There, A New Zealand-born physicist named Ernest Rutherford was about to conduct what would later be called the most beautiful experiment in physics. He didn't know it at the time, but he was about to shatter humanity's understanding of the atom so completely that the pieces would never fit back together the same way. Rutherford's experiment was elegantly simple. He took a thin sheet of gold foil, so thin it was only a few hundred atoms thick, and fired alpha particles at it. Alpha particles are essentially helium nuclei, tiny bullets of matter moving at tremendous speed. According to the prevailing model of the atom developed by J.J. Thomson and known as the plum pudding model, atoms were like soft, squishy balls of positive charge with electrons embedded throughout like raisins in a pudding. If Thomson was right, Rutherford's alpha particles should have passed through the gold foil with only slight deflections, like bullets passing through fog. Instead, what Rutherford observed was so shocking it made him question his own sanity. Most alpha particles did indeed pass straight through, but some bounced back at impossible angles. A few actually reversed direction completely, as if they had hit something incredibly small, but incredibly dense. Rutherford later described his astonishment. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." What Rutherford had discovered was that atoms are almost entirely empty space, with virtually all of their mass concentrated in an incredibly tiny, dense nucleus at the centre. The electrons, he realized, must be orbiting this nucleus like planets around the sun. It was a beautiful model, elegant in its simplicity. There was just one problem. It was physically impossible. Here's why Rutherford's nuclear atom should have been unstable. According to Maxwell's equations, the fundamental laws of electromagnetism that had explained everything from radio waves to light, any charged particle that accelerates must radiate electromagnetic energy. Electrons orbiting a nucleus are constantly accelerating as they change direction in their circular paths. This means they should constantly be radiating energy away, like a leaky bucket losing water. As electrons lose energy, they should spiral inward toward the nucleus, much like a satellite losing altitude falls toward Earth. The calculations were terrifyingly precise. Every atom in the universe should collapse in approximately 100 millionth of a billionth of a second. Matter itself should be impossible, yet matter obviously existed. Atoms were stable. Somehow the electrons managed to orbit the nucleus indefinitely without spiraling inward. Classical physics had no explanation for this stability, and without stable atoms there could be no chemistry, no biology, no life, and certainly no physicists to puzzle over the problem. The crisis was so profound that it threatened the very foundations of physical science. If the fundamental laws of electromagnetism couldn't explain why atoms held together, what could they explain? The scientific community found itself facing a choice. Either Maxwell's equations were wrong, or something entirely new was governing the behavior of matter at the atomic scale. Into this crisis stepped a young Danish physicist named Niels Bohr. In 1913, at the age of 28, Bohr proposed a solution so radical that it seemed to violate everything physicists thought they knew about the natural world. His approach was audacious in its simplicity. He would save the atom by breaking the rules. Bohr began with a bold assumption that would have seemed like heresy to classical physicists. He proposed that electrons in atoms could only occupy certain specific orbits, and that while they remained in these special orbits, they would not radiate energy at all. This wasn't just a minor modification to existing theory. It was a complete rejection of classical electromagnetism when applied to the atomic realm. Think of it this way. Imagine you're climbing a staircase, but this isn't an ordinary staircase. In Bohr's quantum staircase, you can stand on the first step, the second step, or the third step, but you absolutely cannot stand between steps. There is no between in Bohr's atomic world. Electrons could exist in the first allowed orbit, the second allowed orbit, or any other permitted orbit, but they could never exist in the spaces between these orbits. Even more remarkably, Bohr proposed that when electrons moved from one allowed orbit to another, they didn't travel through the intervening space. They simply disappeared from one orbit and instantly appeared in another, like a magician's trick played out on an atomic stage. These instantaneous transitions became known as quantum jumps or quantum leaps, a phrase that has since entered everyday language, though few people realize its origin in the strange world of atomic physics. But Bohr's model wasn't just a collection of arbitrary rules designed to save the atom. It was grounded in the quantum ideas that Max Planck had reluctantly introduced more than a decade earlier. Bohr realized that if energy came in discrete packets, quanta, then perhaps the energy of electrons in atoms was also quantized. Only certain energy levels were allowed, and electrons could only jump between these levels by absorbing or emitting precise amounts of energy. This quantization explained why electrons didn't spiral into the nucleus. In Bohr's model, there was a lowest allowed energy level, the ground state, below which electrons simply could not go. It wasn't that they didn't want to fall further, it was that further didn't exist in the quantum world of the atom. The ground state represented a quantum basement with no floor below it. The mathematical beauty of Bohr's model was breathtaking. Using his quantum rules, he could calculate the exact energies of hydrogen's electron orbits. These calculations matched perfectly with decades of spectroscopic observations that had previously been mysterious. The wavelengths of light that hydrogen atoms absorbed and emitted, their spectral fingerprint, could now be explained as the result of electrons jumping between Bohr's allowed orbits. When an electron jumped from a higher energy orbit to a lower one, it emitted a photon with exactly the right energy to account for the difference between the two levels. When it absorbed a photon of the right energy, it could jump from a lower orbit to a higher one. Suddenly the mysterious lines in hydrogen's spectrum weren't mysterious at all. They were a direct map of the atom's internal quantum structure. Bohr's success with hydrogen opened the floodgates for a new kind of physics, one governed by rules that seemed to come from another universe entirely. These weren't the smooth, continuous laws of classical physics, where every value was possible and every motion was predictable. This was a physics of discrete steps, forbidden regions, and instantaneous transitions that defied common sense. The first and most fundamental rule of Bohr's quantum atom was the quantization of angular momentum. In classical physics, a spinning object can have any amount of angular momentum, the measure of its rotational motion. But in Bohr's atom, electrons could only have angular momentum values that were whole number multiples of Planck's constant divided by 2pi. This seemingly arbitrary restriction was what determined which orbits were allowed and which were forbidden. Think of this quantization like a cosmic speed limit, but instead of limiting velocity, it limited the possible values of angular momentum. Just as you can't drive at 35.7 miles per hour if the speed limit only allows multiples of 10, electrons couldn't orbit with arbitrary angular momentum. Only certain discrete values were permitted by the quantum rules. This quantization had profound consequences. It meant that atoms had discrete energy levels, like rungs on a ladder rather than a smooth ramp. An electron could be on the first rung, the second rung, the third rung, and so on, but it could never be between rungs. The spaces between allowed energy levels were quantum mechanically forbidden territory. The second crucial rule was that electrons in allowed orbits did not radiate electromagnetic energy, despite the fact that they were accelerating charged particles. This was perhaps the most shocking violation of classical physics in Bohr's model. Maxwell's equation said that accelerating charges must radiate energy, but Bohr simply declared that this rule didn't apply to electrons in their allowed quantum orbits. They could orbit indefinitely without losing energy, as long as they stayed in their quantum-approved paths. The third rule governed transitions between orbits. When an electron did change its energy level, it did so instantaneously and discontinuously. There was no smooth gliding from one orbit to another, no gradual acceleration or deceleration. The electron would simply vanish from one orbit and materialize in another, emitting or absorbing a photon in the process. These rules seemed almost mystical in their strangeness, but they worked with uncanny precision. Bohr could calculate the energy levels of hydrogen to extraordinary accuracy, predicting the wavelengths of spectral lines that had puzzled scientists for decades. The Balmer series, the Lyman series, the Paschen series, all of these mysterious patterns in hydrogen's spectrum suddenly made perfect sense as transitions between Bohr's quantized energy levels. But the implications went far beyond hydrogen. If atoms had discrete energy levels, then chemistry itself was fundamentally quantum mechanical. The way atoms bonded to form molecules, the colors they emitted when heated, the way they absorbed light, all of these phenomena were expressions of underlying quantum rules that had no classical analogue. Consider what this meant for our understanding of matter. Every chemical reaction, from the burning of wood to the processes of life itself, was really a dance of electrons jumping between quantized energy levels. The energy released when gasoline burns in your car's engine comes from electrons rearranging themselves among the allowed quantum states of different atoms and molecules. The very fact that different elements have different chemical properties stems from their unique quantum energy level structures. As Bohr's model gained acceptance, physicists realized they had stumbled upon something far more profound than just a theory of atomic structure. They had discovered that the atomic world was a natural laboratory for quantum mechanics, where the strange new rules of quantum physics played out in measurable, observable ways. Spectroscopy, the study of how atoms absorb and emit light, became quantum mechanics' testing ground. Every spectral line represented a quantum transition, a leap between discrete energy levels that could be calculated using Bohr's rules. Scientists could literally see quantum mechanics at work by analyzing the light coming from atoms. The precision was astounding. Using quantum theory, physicists could predict the exact wavelength of light that would be emitted when a hydrogen electron jumped from the third energy level to the second, or from the fifth to the first. These predictions matched experimental observations to several decimal places, providing compelling evidence that Bohr's quantum rules weren't just mathematical curiosities, they were fundamental laws of nature. But spectroscopy revealed something even more remarkable. Each element had its own unique spectral fingerprint, its own distinctive pattern of absorption and emission lines. This fingerprint was so reliable that astronomers could determine the composition of distant stars simply by analyzing their light. The same quantum rules that governed atoms in earthly laboratories also operated in the hearts of stars billions of miles away. This universality of quantum behavior was perhaps the most profound revelation of all. The quantum rules weren't some strange aberration limited to specially prepared laboratory samples. They were fundamental features of reality itself, operating everywhere from the smallest atoms to the largest stars. The universe, it seemed, was quantum mechanical all the way down. The periodic table, too, took on new meaning in light of Bohr's quantum atom. Why did elements with similar numbers of electrons in their outer shells have similar chemical properties? The answer lay in quantum mechanics. Elements in the same column of the periodic table had similar quantum configurations in their outermost electron shells, leading to similar chemical behavior. Sodium and potassium, for example, both have one electron in their outermost quantum shell, making them highly reactive metals with similar properties. Helium and neon both have completely filled outer quantum shells, making them chemically inert noble gases. What had once seemed like arbitrary patterns in the periodic table were actually expressions of underlying quantum structure. Chemistry itself was revealed to be applied quantum mechanics. The way atoms bonded together to form molecules, the shapes of molecular structures, the energies of chemical reactions, all of these phenomena were consequences of electrons occupying quantized energy levels and following quantum rules when they interacted with other atoms. Even the colors we see around us are quantum mechanical in origin. The deep red of a ruby comes from chromium atoms whose electrons make specific quantum transitions when stimulated by light. The brilliant blue of a sapphire results from different quantum transitions in iron and titanium atoms. Every hue in nature's palette is ultimately a manifestation of quantum mechanics playing out in the atomic realm. Yet even as Bohr's model achieved spectacular success in explaining hydrogen and providing insights into the periodic table, it carried within itself the seeds of its own limitation. The very arbitrariness of its rules, the ad hoc way Bohr had simply declared that certain classical laws didn't apply to electrons in atoms, suggested that this was not the final word on quantum mechanics. Why were only certain orbits allowed? Why didn't electrons radiate when they were in these special orbits? Why did quantum jumps happen instantaneously? Bohr's model provided no deep answers to these questions. It worked, and it worked brilliantly, but it felt more like a collection of successful guesses than a fundamental theory. The model also failed when applied to atoms more complex than hydrogen. Helium, with its 2 electrons, proved surprisingly difficult to analyze using Bohr's methods. The quantum rules that worked so perfectly for hydrogen's single electron became unwieldy and imprecise when multiple electrons were involved. It was becoming clear that Bohr's model, revolutionary as it was, represented only the first step toward a more complete quantum theory. Perhaps most troubling of all was the model's uncomfortable relationship with classical physics. Bohr had saved the atom by essentially declaring that classical electromagnetism didn't apply to electrons in their allowed orbits, but this raised profound questions about the nature of physical law itself. Were there 2 different sets of physical laws, one for the quantum world and another for the everyday world? At what point did classical physics take over from quantum mechanics? These questions would torment physicists for the next decade, driving them to search for a more complete and self-consistent quantum theory. They needed a framework that didn't just work by arbitrary decree, but one that could explain why the quantum rules existed in the first place. They needed to understand not just what happened in the atomic world, but why it happened that way. The stage was set for the next great quantum revolution. Bohr had shown that atoms were quantum mechanical, but he hadn't yet revealed the deeper mathematical structure that governed quantum behavior. That revelation would come from an unexpected source, a young German physicist suffering from hay fever, working alone on a windswept island in the North Sea, who would discover that the quantum world operated according to mathematical rules so strange they would challenge the very foundations of reality itself. But that discovery lay ahead. For now, in 1913, Bohr had accomplished something remarkable. He had saved the atom from theoretical annihilation, and in doing so had opened the door to the quantum age. The atomic theatre was no longer a stage for classical physics, with its predictable trajectories and continuous motions. It had become something far stranger and more wonderful, a quantum stage where electrons performed impossible leaps, where energy came in discrete packets, and where the very act of observation would soon be discovered to change the nature of what was being observed. The atom was safe, but reality would never be the same. Chapter 5. The Atomic Theatre. You're holding a penny in your hand. That small copper disc contains roughly 30 billion trillion atoms. Each one of those atoms should, according to everything scientists understood in 1910, collapse in on itself in less than a trillionth of a second. The electrons orbiting each atomic nucleus should spiral inward like water going down a drain, radiating away their energy until they crash into the nucleus and annihilate the atom entirely. By all rights, that penny and you and everything in the universe should have ceased to exist before you could even blink. Yet here you are, and here it is. The fact that atoms exist at all presented early 20th century physics with what seemed like an impossible paradox. The solution to this paradox would not only save the atom from theoretical destruction, it would launch quantum mechanics into a realm so strange that even today, more than a century later, we're still grappling with its implications. To understand how desperate the situation had become, we need to travel back to 1909 to a basement laboratory at Manchester University in England. There, a New Zealand-born physicist named Ernest Rutherford was about to conduct what would later be called the most beautiful experiment in physics. He didn't know it at the time, but he was about to shatter humanity's understanding of the atom so completely that the pieces would never fit back together the same way. Rutherford's experiment was elegantly simple. He took a thin sheet of gold foil, so thin it was only a few hundred atoms thick, and fired alpha particles at it. Alpha particles are essentially helium nuclei, tiny bullets of matter moving at tremendous speed. According to the prevailing model of the atom, developed by J.J. Thomson and known as the plum pudding model, atoms were like soft, squishy balls of positive charge, with electrons embedded throughout like raisins in a pudding. If Thomson was right, Rutherford's alpha particles should have passed through the gold foil with only slight deflections, like bullets passing through fog. Instead, what Rutherford observed was so shocking it made him question his own sanity. Most alpha particles did indeed pass straight through, but some bounced back at impossible angles. A few actually reversed direction completely, as if they had hit something incredibly small but incredibly dense. Rutherford later described his astonishment. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." What Rutherford had discovered was that atoms are almost entirely empty space, with virtually all of their mass concentrated in an incredibly tiny, dense nucleus at the center. The electrons, he realized, must be orbiting this nucleus like planets around the sun. It was a beautiful model, elegant in its simplicity. There was just one problem. It was physically impossible. Here's why Rutherford's nuclear atom should have been unstable. According to Maxwell's equations, the fundamental laws of electromagnetism that had explained everything from radio waves to light, any charged particle that accelerates must radiate electromagnetic energy. Electrons orbiting a nucleus are constantly accelerating as they change direction in their circular paths. This means they should constantly be radiating energy away, like a leaky bucket losing water. As electrons lose energy, they should spiral inward toward the nucleus, much like a satellite losing altitude falls toward Earth. The calculations were terrifyingly precise. Every atom in the universe should collapse in approximately 100 millionth of a billionth of a second. Matter itself should be impossible. Yet matter obviously existed. Atoms were stable. Somehow the electrons managed to orbit the nucleus indefinitely without spiraling inward. Classical physics had no explanation for this stability, and without stable atoms there could be no chemistry, no biology, no life, and certainly no physicists to puzzle over the problem. The crisis was so profound that it threatened the very foundations of physical science. If the fundamental laws of electromagnetism couldn't explain why atoms held together, what could they explain? The scientific community found itself facing a choice. Either Maxwell's equations were wrong, or something entirely new was governing the behavior of matter at the atomic scale. Into this crisis stepped a young Danish physicist named Niels Bohr. In 1913, at the age of 28, Bohr proposed a solution so radical that it seemed to violate everything physicists thought they knew about the natural world. His approach was audacious in its simplicity. He would save the atom by breaking the rules. Bohr began with a bold assumption that would have seemed like heresy to classical physicists. He proposed that electrons in atoms could only occupy certain specific orbits, and that while they remained in these special orbits, they would not radiate energy at all. This wasn't just a minor modification to existing theory. It was a complete rejection of classical electromagnetism when applied to the atomic realm. Think of it this way. Imagine you're climbing a staircase, but this isn't an ordinary staircase. In Bohr's quantum staircase, you can stand on the first step, the second step, or the third step, but you absolutely cannot stand between steps. There is no between in Bohr's atomic world. Electrons could exist in the first allowed orbit, the second allowed orbit, or any other permitted orbit, but they could never exist in the spaces between these orbits. Even more remarkably, Bohr proposed that when electrons moved from one allowed orbit to another, they didn't travel through the intervening space. They simply disappeared from one orbit and instantly appeared in another, like a magician's trick played out on an atomic stage. These instantaneous transitions became known as quantum jumps or quantum leaps, a phrase that has since entered everyday language, though few people realize its origin in the strange world of atomic physics. But Bohr's model wasn't just a collection of arbitrary rules designed to save the atom. It was grounded in the quantum ideas that Max Planck had reluctantly introduced more than a decade earlier. Bohr realized that if energy came in discrete packets, quanta, then perhaps the energy of electrons in atoms was also quantized. Only certain energy levels were allowed, and electrons could only jump between these levels by absorbing or emitting precise amounts of energy. This quantization explained why electrons didn't spiral into the nucleus. In Bohr's model, there was a lowest allowed energy level, the ground state, below which electrons simply could not go. It wasn't that they didn't want to fall further, it was that further didn't exist in the quantum world of the atom. The ground state represented a quantum basement with no floor below it. The mathematical beauty of Bohr's model was breathtaking. Using his quantum rules, he could calculate the exact energies of hydrogen's electron orbits. These calculations matched perfectly with decades of spectroscopic observations that had previously been mysterious. The wavelengths of light that hydrogen atoms absorbed and emitted, their spectral fingerprint, could now be explained as the result of electrons jumping between Bohr's allowed orbits. When an electron jumped from a higher energy orbit to a lower one, it emitted a photon with exactly the right energy to account for the difference between the two levels. When it absorbed a photon of the right energy, it could jump from a lower orbit to a higher one. Suddenly, the mysterious lines in hydrogen's spectrum weren't mysterious at all. They were a direct map of the atom's internal quantum structure. Bohr's success with hydrogen opened the floodgates for a new kind of physics, one governed by rules that seemed to come from another universe entirely. These weren't the smooth, continuous laws of classical physics, where every value was possible and every motion was predictable. This was a physics of discrete steps, forbidden regions and instantaneous transitions that defied common sense. The first and most fundamental rule of Bohr's quantum atom was the quantization of angular momentum. In classical physics, a spinning object can have any amount of angular momentum, the measure of its rotational motion. But in Bohr's atom, electrons could only have angular momentum values that were whole number multiples of Planck's constant, divided by 2pi. This seemingly arbitrary restriction was what determined which orbits were allowed and which were forbidden. Think of this quantization like a cosmic speed limit, but instead of limiting velocity, it limited the possible values of angular momentum. Just as you can't drive at 35.7 miles per hour if the speed limit only allows multiples of 10, electrons couldn't orbit with arbitrary angular momentum, only certain discrete values were permitted by the quantum rules. This quantization had profound consequences. It meant that atoms had discrete energy levels, like rungs on a ladder rather than a smooth ramp. An electron could be on the first rung, the second rung, the third rung, and so on. But it could never be between rungs. The spaces between allowed energy levels were quantum mechanically forbidden territory. The second crucial rule was that electrons in allowed orbits did not radiate electromagnetic energy, despite the fact that they were accelerating charged particles. This was perhaps the most shocking violation of classical physics in Bohr's model. Maxwell's equations said that accelerating charges must radiate energy, but Bohr simply declared that this rule didn't apply to electrons in their allowed quantum orbits. They could orbit indefinitely without losing energy, as long as they stayed in their quantum-approved paths. The third rule governed transitions between orbits. When an electron did change its energy level, it did so instantaneously and discontinuously. There was no smooth gliding from one orbit to another, no gradual acceleration or deceleration. The electron would simply vanish from one orbit and materialize in another, emitting or absorbing a photon in the process. These rules seemed almost mystical in their strangeness, but they worked with uncanny precision. Bohr could calculate the energy levels of hydrogen to extraordinary accuracy, predicting the wavelengths of spectral lines that had puzzled scientists for decades. The Balmer series, the Lyman series, the Paschen series, all of these mysterious patterns in hydrogen's spectrum suddenly made perfect sense as transitions between Bohr's quantized energy levels. But the implications went far beyond hydrogen. If atoms had discrete energy levels, then chemistry itself was fundamentally quantum mechanical. The way atoms bonded to form molecules, the colors they emitted when heated, the way they absorbed light, all of these phenomena were expressions of underlying quantum rules that had no classical analog. Consider what this meant for our understanding of matter. Every chemical reaction, from the burning of wood to the processes of life itself, was really a dance of electrons jumping between quantized energy levels. The energy released when gasoline burns in your car's engine comes from electrons rearranging themselves among the allowed quantum states of different atoms and molecules. The very fact that different elements have different chemical properties stems from their unique quantum energy level structures. As Bohr's model gained acceptance, physicists realized they had stumbled upon something far more profound than just a theory of atomic structure. They had discovered that the atomic world was a natural laboratory for quantum mechanics, where the strange new rules of quantum physics played out in measurable, observable ways. Spectroscopy, the study of how atoms absorb and emit light, became quantum mechanics' testing ground. Every spectral line represented a quantum transition, a leap between discrete energy levels that could be calculated using Bohr's rules. Scientists could literally see quantum mechanics at work by analyzing the light coming from atoms. The precision was astounding. Using quantum theory, physicists could predict the exact wavelength of light that would be emitted when a hydrogen electron jumped from the third energy level to the second, or from the fifth to the first. These predictions matched experimental observations to several decimal places, providing compelling evidence that Bohr's quantum rules weren't just mathematical curiosities, they were fundamental laws of nature. But spectroscopy revealed something even more remarkable. Each element had its own unique spectral fingerprint, its own distinctive pattern of absorption and emission lines. This fingerprint was so reliable that astronomers could determine the composition of distant stars simply by analyzing their light. The same quantum rules that governed atoms in earthly laboratories also operated in the hearts of stars billions of miles away. This universality of quantum behavior was perhaps the most profound revelation of all. The quantum rules weren't some strange aberration limited to specially prepared laboratory samples. They were fundamental features of reality itself, operating everywhere from the smallest atoms to the largest stars. The universe, it seemed, was quantum mechanical all the way down. The periodic table, too, took on new meaning in light of Bohr's quantum atom. Why did elements with similar numbers of electrons in their outer shells have similar chemical properties? The answer lay in quantum mechanics. Elements in the same column of the periodic table had similar quantum configurations in their outermost electron shells, leading to similar chemical behavior. Sodium and potassium, for example, both have one electron in their outermost quantum shell, making them highly reactive metals with similar properties. Helium and neon both have completely filled outer quantum shells, making them chemically inert noble gases. What had once seemed like arbitrary patterns in the periodic table were actually expressions of underlying quantum structure. Chemistry itself was revealed to be applied quantum mechanics. The way atoms bonded together to form molecules, the shapes of molecular structures, the energies of chemical reactions, all of these phenomena were consequences of electrons occupying quantized energy levels and following quantum rules when they interacted with other atoms. Even the colors we see around us are quantum mechanical in origin. The deep red of a ruby comes from chromium atoms whose electrons make specific quantum transitions when stimulated by light. The brilliant blue of a sapphire results from different quantum transitions in iron and titanium atoms. Every hue in nature's palette is ultimately a manifestation of quantum mechanics playing out in the atomic realm. Yet even as Bohr's model achieved spectacular success in explaining hydrogen and providing insights into the periodic table, it carried within itself the seeds of its own limitation. The very arbitrariness of its rules, the ad hoc way Bohr had simply declared that certain classical laws didn't apply to electrons in atoms, suggested that this was not the final word on quantum mechanics. Why were only certain orbits allowed? Why didn't electrons radiate when they were in these special orbits? Why did quantum jumps happen instantaneously? Bohr's model provided no deep answers to these questions. It worked, and it worked brilliantly, but it felt more like a collection of successful guesses than a fundamental theory. The model also failed when applied to atoms more complex than hydrogen. Helium, with its 2 electrons, proved surprisingly difficult to analyze using Bohr's methods. The quantum rules that worked so perfectly for hydrogen's single electron became unwieldy and imprecise when multiple electrons were involved. It was becoming clear that Bohr's model, revolutionary as it was, represented only the first step toward a more complete quantum theory. Perhaps most troubling of all was the model's uncomfortable relationship with classical physics. Bohr had saved the atom by essentially declaring that classical electromagnetism didn't apply to electrons in their allowed orbits, but this raised profound questions about the nature of physical law itself. Were there 2 different sets of physical laws, one for the quantum world and another for the everyday world? At what point did classical physics take over from quantum mechanics? These questions would torment physicists for the next decade, driving them to search for a more complete and self-consistent quantum theory. They needed a framework that didn't just work by arbitrary decree, but one that could explain why the quantum rules existed in the first place. They needed to understand not just what happened in the atomic world, but why it happened that way. The stage was set for the next great quantum revolution. Bohr had shown that atoms were quantum mechanical, but he hadn't yet revealed the deeper mathematical structure that governed quantum behavior. That revelation would come from an unexpected source, a young German physicist suffering from hay fever, working alone on a windswept island in the North Sea, who would discover that the quantum world operated according to mathematical rules so strange they would challenge the very foundations of reality itself. But that discovery lay ahead. For now, in 1913, Bohr had accomplished something remarkable. He had saved the atom from theoretical annihilation, and in doing so had opened the door to the quantum age. The atomic theatre was no longer a stage for classical physics, with its predictable trajectories and continuous motions. It had become something far stranger and more wonderful, a quantum stage where electrons performed impossible leaps, where energy came in discrete packets, and where the very act of observation would soon be discovered to change the nature of what was being observed. The atom was safe, but reality would never be the same. Chapter 6. The Matrix Revolution. A 25-year-old physicist, eyes watering and nose running from a severe bout of hay fever, sits alone on a rocky island in the North Sea. The year is 1925, and Werner Heisenberg has fled to the barren landscape of Helgoland to escape the pollen that torments him on the German mainland. He's brought with him one of the most perplexing puzzles in all of science. Why do atoms behave the way they do? What he doesn't know is that over the next few sleepless nights, between sneezing fits and walks along the windswept cliffs, he's about to crack open the very foundations of reality itself. This is the story of how hay fever helped birth the first complete quantum theory, and how a young man's mathematical revolution would forever change what it means to know anything about the universe around us. Werner Heisenberg was not your typical revolutionary. Unlike Einstein, who challenged physics with bold thought experiments and philosophical insights, Heisenberg was a mathematician's mathematician, precise, methodical, and utterly practical. Born in 1901 in Bavaria, he had already shown himself to be a prodigy, completing his doctoral thesis under Arnold Sommerfeld on turbulence in fluid flow. But it was his fascination with the mysterious behavior of atoms that would make him immortal. By 1925, atomic physics was in crisis. Scientists could observe what atoms did. They emitted light in precise patterns. They absorbed energy in specific amounts. They seemed to jump between states without traveling through the space in between. But nobody could explain why these things happened. The old physics, the classical mechanics that had worked so beautifully for planets and pendulums, simply broke down when applied to the atomic world. Heisenberg had been wrestling with this problem for months, when his hay fever drove him to seek refuge on Helgoland, a small rocky island about 40 miles off the German coast. The island was bleak and windswept, but it was mercifully free of the pollen that made his life miserable every spring. Here, in a sparse rented room overlooking the North Sea, Heisenberg decided to try something radical. Instead of trying to picture what was happening inside atoms, instead of trying to imagine tiny particles orbiting like miniature solar systems, he would focus only on what could actually be observed and measured. He would build a theory based purely on the numbers that came out of experiments, the frequencies of light that atoms emitted, the intensities of spectral lines, the energy levels that could be measured in the laboratory. This sounds simple, but it was actually a profound philosophical shift. For centuries, physicists had tried to understand nature by building mental pictures of how things worked. They imagined atoms as tiny billiard balls or electrons as particles following definite paths. Heisenberg was proposing to abandon all of that, to build a theory that described atomic behavior without ever trying to visualize what atoms actually looked like. Night after night, as he walked the island's rocky paths under the stars, Heisenberg began to see how this might work. He realized that the key was to focus on the transitions between atomic states rather than the states themselves. When an atom emitted light, it was jumping from one energy level to another. The frequency and intensity of that light depended on both the initial and final states. What mattered wasn't the individual states, but the relationships between them. But here's where Heisenberg's story takes an almost mystical turn. On the night when his breakthrough came, he barely slept. He spent hours walking the island, thinking through the mathematical implications of his new approach. When he finally returned to his room and began working through the calculations, something extraordinary happened. The mathematics that emerged was unlike anything he had seen before. It worked. It predicted the correct frequencies and intensities of atomic spectra, but it was built on a strange mathematical foundation where the order of multiplication mattered in ways it never had before. In normal arithmetic, 2 times 3 equals 3 times 2. But in Heisenberg's quantum mathematics, multiplying quantity A by quantity B could give a completely different result than multiplying B by A. This wasn't a mistake or an approximation, it was a fundamental feature of the theory. The universe itself, at its deepest level, seemed to operate according to mathematical rules where order mattered in previously unimaginable ways. As dawn broke over the North Sea, Heisenberg realized he had discovered something that would change physics forever. But he also sensed that he had uncovered something disturbing about the nature of reality itself. When Heisenberg returned to the mainland, He faced a problem that every revolutionary encounters. How do you explain a completely new way of thinking to people who are still trapped in the old way? His mathematical breakthrough was so radical that even he didn't fully understand what he had discovered. The numbers worked, his calculations perfectly predicted atomic behavior, but the mathematics seemed to come from another universe. This is where the story becomes a collaboration between three brilliant minds. Heisenberg took his strange new mathematics to his mentor, Max Born, at the University of Göttingen. Born was one of those rare physicists who was equally at home with abstract mathematics and concrete physical intuition. When he saw Heisenberg's work, he immediately recognized something that the younger physicist had missed. The mathematical structures that Heisenberg had stumbled upon were matrices. Now, matrices might sound like something from a science fiction movie, but they're actually quite simple mathematical objects. Rectangular arrays of numbers that follow specific rules for multiplication. What made them perfect for quantum mechanics was precisely the property that had puzzled Heisenberg. When you multiply matrices, the order matters. Matrix A times matrix B is generally not the same as matrix B times matrix A. Born realized that this wasn't a quirk of Heisenberg's mathematics. It was a fundamental statement about the physical world. In the quantum realm, the order in which you measure things affects what you find. If you measure an electron's position and then its momentum, you get a different result than if you measure its momentum first and then its position. The universe itself is built on mathematics where order matters. Working with another brilliant young physicist, Pascual Jordan, Born helped Heisenberg transform his intuitive breakthrough into a complete mathematical theory. They called it matrix mechanics, and it was the first fully consistent quantum theory in history. Every aspect of atomic behavior, energy levels, spectral lines, chemical bonding, could be calculated using their matrix mathematics. But here's what made matrix mechanics so revolutionary. It completely abandoned the classical picture of atoms as tiny solar systems. There were no electron orbits in this theory, no definite paths, no clear positions or velocities. Instead, there were only matrices, mathematical objects that encoded the probabilities of finding specific results when measurements were made. Think about what this means. For thousands of years, humans had tried to understand nature by imagining how things looked and moved. We pictured the solar system as planets following elliptical paths around the sun. We imagined atoms as miniature solar systems with electrons orbiting the nucleus. Matrix mechanics said, forget all of that. Nature doesn't consist of objects moving along definite paths. Instead, nature consists of probabilities, relationships, and the mathematical structures that connect observable quantities. This was more than a new theory. It was a completely new way of thinking about reality, and it worked with stunning precision. Matrix mechanics could predict the exact frequencies of light emitted by hydrogen atoms, the chemical properties of different elements, the behavior of atoms in magnetic fields. For the first time in history, scientists had a theory that could make precise, quantitative predictions about atomic behavior, but success came with a cost. The price of this predictive power was giving up the comfortable notion that we could visualize what atoms actually looked like. In matrix mechanics, atoms didn't have a definite appearance at all. They were mathematical abstractions, collections of probabilities and relationships that only became concrete when measurements were made. This philosophical challenge was just the beginning. As Heisenberg continued to explore the implications of his theory, he discovered something even more disturbing about the nature of quantum reality. 2 years after his breakthrough on Helgoland, Heisenberg made another discovery that would shake the scientific world even more profoundly than matrix mechanics. This time, there was no romantic island retreat, no dramatic moment of inspiration. Instead, there was just Heisenberg, working late at night in his laboratory, trying to understand what his own equations were telling him about the limits of measurement. The question that obsessed him was this: if you could build a perfect microscope, one that could see individual electrons, what would limit how precisely you could measure an electron's position and velocity? This might seem like a purely technical question, but Heisenberg realized it went to the heart of what it means to know anything about the physical world. His analysis led him to a conclusion so startling that even he initially resisted it. There is a fundamental limit to how precisely you can simultaneously know both the position and momentum of any quantum particle. This wasn't due to imperfect instruments or clumsy measurement techniques. It was a basic feature of reality itself. The mathematics was crystal clear. If you measure an electron's position very precisely, you inevitably disturb its momentum in an unpredictable way. If you measure its momentum precisely, you unavoidably disturb its position. The more precisely you know one quantity, the less precisely you can know the other. And this trade-off is governed by Planck's constant, that tiny number that had emerged from black-body radiation and now revealed itself as a fundamental feature of all quantum measurements. This is what we now call the Heisenberg uncertainty principle, and it represents one of the most profound discoveries in the history of science. Heisenberg had shown that uncertainty isn't just a practical limitation, it's woven into the fabric of reality itself. But here's what makes the uncertainty principle truly revolutionary. It's not really about measurement at all. It's about the nature of quantum objects themselves. An electron doesn't have a definite position and momentum that we simply can't measure precisely. Rather, an electron doesn't have definite position and momentum, period. These properties only come into existence when we make measurements, and the act of measurement inevitably creates uncertainty in unmeasured quantities. Think about what this means for our understanding of reality. In the classical world, we assume that objects have definite properties whether we observe them or not. A baseball has a specific position and velocity even when no one is watching it. But in the quantum world, particles exist in a strange limbo of undefined properties until the moment of measurement. Einstein was deeply troubled by this conclusion. In 1927, at the famous Solvay conference in Brussels, he engaged in heated debates with Heisenberg and Bohr about the implications of the uncertainty principle. Einstein's famous comment that God does not play dice with the universe was specifically directed at the fundamental randomness that the uncertainty principle seemed to introduce into physics. But Heisenberg had an elegant response. He pointed out that the uncertainty principle didn't make physics less precise, it made precision itself more precisely defined. By showing exactly what could and couldn't be known simultaneously, the uncertainty principle actually made quantum mechanics more rigorous and predictive than classical physics had ever been. Consider the profound philosophical implications. For centuries, scientists had dreamed of a complete description of nature, a theory that could, in principle, predict the exact future of every particle in the universe. The uncertainty principle showed that this dream was not just impractical, but fundamentally impossible. Nature itself places limits on what can be known. Yet paradoxically, these limits didn't make physics weaker, they made it stronger. By acknowledging the boundaries of knowledge, quantum mechanics achieved predictive power that surpassed anything classical physics had accomplished. The uncertainty principle wasn't a limitation of the theory, it was the key to its success. But the story of quantum measurement was far from over. As Heisenberg would soon discover, the act of observation itself played a role in quantum mechanics that no one had anticipated. The uncertainty principle had revealed that measurement disturbs quantum systems in fundamental ways, but Heisenberg's next insight was even more disturbing. The very act of measurement seemed to play a creative role in quantum reality. This wasn't just a practical concern about experimental technique. It suggested that consciousness itself might be woven into the basic structure of the physical world. To understand how Heisenberg arrived at this unsettling conclusion, imagine trying to see an electron. This sounds simple enough. After all, we see objects all the time by observing the light that bounces off them. But when you try to apply this common-sense approach to electrons, you immediately run into problems that reveal the strange nature of the quantum world. To see an electron, you need to bounce at least one photon of light off it. But here's the problem. A photon carries energy and momentum. When it hits an electron, it inevitably changes the electron's motion in unpredictable ways. This isn't because our instruments are clumsy. It's because any interaction energetic enough to reveal information about the electron necessarily disturbs the electron. Heisenberg worked through this thought experiment with mathematical precision. He imagined a microscope capable of seeing individual electrons, and he calculated exactly how the act of observation would affect what was being observed. What he found was that the disturbance wasn't just unavoidable, it was precisely correlated with the information gained. The more precisely you tried to measure the electron's position, the more violently you disrupted its momentum, and vice versa. But this raised a deeper question that went to the heart of quantum mechanics. What happens to quantum systems when they're not being observed? If measurement inevitably changes quantum systems, what are these systems like in their natural, unobserved state? Heisenberg's equations suggested something almost unthinkable. Quantum systems don't have definite properties when they're not being measured. An electron doesn't have a specific position and momentum that we disturb when we observe it. Instead, an electron exists in what we now call a quantum superposition, a strange limbo where all possible positions and momenta coexist simultaneously. This idea was so radical that even Heisenberg struggled to accept its implications. It seemed to suggest that the act of measurement doesn't just reveal pre-existing properties, it actually creates properties that didn't exist before. When you measure an electron's position, you don't just find where it is, you make it be somewhere specific. The implications were staggering. If consciousness, the act of observation, played a creative role in quantum reality, then the boundary between mind and matter began to blur in unprecedented ways. Some physicists began to wonder whether quantum mechanics revealed something fundamental about the role of consciousness in the physical world. Consider what this means for our understanding of reality. In the classical world, we assume that objects have definite properties independent of observation. The moon has a specific position and velocity whether anyone is looking at it or not. But quantum mechanics seem to suggest that, at least for microscopic systems, properties only come into existence through the act of measurement. This observer effect became one of the most philosophically challenging aspects of quantum mechanics. It suggested that the universe wasn't a machine running independently of conscious observers. Instead, consciousness and physical reality seemed to be intimately connected in ways that classical physics had never imagined. Einstein found this conclusion deeply troubling. He argued that physical reality must exist independently of observation, that the moon is there whether we look at it or not. But Heisenberg's analysis suggested that this common-sense assumption might not apply to the quantum world. The debate over the observer effect continues to this day. Some physicists argue that consciousness plays no special role, that any physical interaction, conscious or not, can trigger the transition from quantum superposition to definite properties. Others maintain that consciousness is indeed special, and that the act of conscious observation is what transforms quantum possibilities into classical realities. What everyone agreed on was that Heisenberg had uncovered something profound about the relationship between knowledge and reality. In the quantum world, the act of gaining information inevitably changes what you're trying to learn about. Observer and observed are connected in ways that make them impossible to separate completely. This interconnectedness would soon lead to even stranger discoveries about the nature of quantum reality. But first, the physics community had to grapple with what Heisenberg had already revealed. That uncertainty wasn't a limitation of our theories, it was a fundamental feature of nature itself, and one that placed consciousness at the very center of physical reality. As word of Heisenberg's discoveries spread through the physics community, one thing became clear. The comfortable classical world of definite objects with definite properties was gone forever. In its place was a quantum reality, where uncertainty, measurement and observation played central roles in determining what could be known about the nature of things. The implications would only become stranger as other physicists began to explore what this new quantum reality meant for our understanding of the universe itself. But that's a story for the next chapter of our quantum journey, a story that would involve a cat, a thought experiment, and one of the most famous paradoxes in all of science. Chapter 7. The Wave Dreamer. It's Christmas Day, 1925, and while families across Europe are unwrapping presents and sharing festive meals, a brilliant Austrian physicist named Erwin Schrödinger is holed up in a villa in the Swiss Alps with his mistress, wrestling with what would become the most important equation in quantum mechanics. What he discovered during those passionate, intellectually fevered weeks wouldn't just change physics, it would reveal that reality itself is built from waves of pure possibility. But here's the twist that makes this story even more extraordinary. Schrödinger absolutely hated where his own equation led him. The man who gave us the mathematical foundation of quantum mechanics spent the rest of his life trying to prove that quantum mechanics made no sense at all. And in his frustration, he would create the most famous thought experiment in scientific history. A cat that is simultaneously dead and alive, existing in a ghostly limbo until someone dares to look. This is the story of how wave mechanics was born from passion and genius, how it revealed the strangest truth about our universe, and how its creator became quantum mechanics' most eloquent critic. The winter of 1925 found Schrödinger in a peculiar position. He was 38 years old, considered past his prime in the youth-obsessed world of theoretical physics, watching as brilliant 20-somethings like Heisenberg revolutionized the field with their abstract matrix mathematics. Schrödinger found Heisenberg's approach deeply unsatisfying. It was all about numbers and calculations, with no intuitive picture of what was actually happening inside an atom. Then in late 1925, Schrödinger attended a seminar where a colleague discussed Louis de Broglie's radical idea that particles might also be waves. Most physicists had dismissed de Broglie's thesis as mathematical speculation, but something about it captured Schrödinger's imagination. If electrons really were waves, perhaps there was a way to describe atomic behavior that made physical sense, unlike Heisenberg's abstract matrices. So Schrödinger retreated to his favorite villa in Arosa, Switzerland, bringing along what his biographers delicately describe as inspiration, both intellectual and personal. Working with intense focus through the Christmas holidays, he began developing a wave equation that could describe the behavior of these hypothetical matter waves. What emerged from those weeks was breathtaking in its mathematical beauty and conceptual power. Schrödinger's wave equation could predict the energy levels of hydrogen atoms with perfect accuracy, matching every experimental observation. But unlike Heisenberg's matrices, Schrödinger's waves seemed to offer an intuitive picture. Electrons weren't particles orbiting the nucleus, they were standing waves, like the vibrations of a violin string resonating around the atomic core. The equation itself appeared almost mystically elegant. It connected the energy of a quantum system to the curvature of its wave function through a mathematical relationship so fundamental that it seemed to capture something essential about the structure of reality itself. When Schrödinger first derived it, he reportedly said it was so beautiful that it had to be right. But as 1926 progressed, and Schrödinger explored the implications of his equation, a troubling question emerged. What exactly were these waves? They weren't waves in any physical medium. They existed in an abstract mathematical space that had no clear connection to the real world. The more successful his equation became at predicting experimental results, the more mysterious its fundamental meaning appeared. To understand how Schrödinger's waves could make sense, we need to step back to 1924, and a young French aristocrat named Louis de Broglie, who was working on perhaps the most audacious doctoral thesis in the history of physics. Einstein had shown that light waves could behave like particles, photons with discrete energy and momentum. De Broglie asked the obvious but revolutionary question, if waves can act like particles, why can't particles act like waves? The mathematics was surprisingly straightforward. If you take Einstein's famous equation relating energy and mass, combine it with Planck's quantum formula, and apply it to a particle like an electron, you get a wavelength, a specific distance that characterizes the wave nature of that particle. For an electron moving at typical speeds inside an atom, this de Broglie wavelength turns out to be roughly the size of the atom itself. This wasn't just mathematical speculation. In 1927, just 2 years after Schrödinger developed his equation, Clinton Davison and Lester Germer conducted an experiment that proved electrons really do behave like waves. They fired a beam of electrons at a nickel crystal and observed something that should have been impossible if electrons were simply particles: an interference pattern. The telltale signature of waves overlapping and reinforcing or cancelling each other out. Think about what this means. Every electron in your body right now has a wavelength. The atoms that make up your cells are held together by electrons that exist as standing waves, vibrating in precise mathematical harmonies around atomic nuclei. Matter isn't made of tiny billiard balls, it's made of music, mathematical symphonies playing out at scales too small for us to perceive directly. But de Broglie's matter waves led to an even stranger realization. When you try to observe an electron's wave nature, you have to interact with it, and that interaction inevitably involves exchanging at least one photon, one quantum of light. But photons carry momentum, so the very act of observation changes the electron's motion. You can see the electron's wave properties or its particle properties, but never both simultaneously with perfect precision. This wasn't a limitation of measurement technology. It was a fundamental feature of reality. The wave-particle duality that had puzzled physicists for centuries wasn't a contradiction to be resolved. It was nature's deepest truth. Matter and energy exist in a quantum superposition of wave and particle states until the moment they interact with something else. Now we come to the heart of Schrödinger's achievement, the equation that bears his name and governs every quantum mechanical system in the universe. At first glance it looks deceptively simple. Just a mathematical statement relating the energy of a system to the rate at which its wave function changes over time. But hidden within this elegance is a description of reality so profound that it fundamentally changed how we understand the nature of existence itself. The Schrödinger equation tells us that every quantum system, every electron, every atom, every molecule is described by a wave function, usually represented by the Greek letter psi. This wave function isn't a physical wave rippling through space. It's something far more abstract and far more powerful. It's a mathematical object that encodes all possible information about a quantum system in a form that evolves according to precise mathematical rules. Here's where it gets truly strange. The wave function doesn't tell you where an electron is or how fast it's moving. Instead, it tells you the probability of finding the electron at any particular location if you choose to measure it. Before measurement, the electron doesn't have a definite position. Its wave function spreads out across all possible locations with different probabilities for each one. The electron exists in what physicists call a superposition of all possible states simultaneously. When Schrödinger first realized this implication of his own equation, he was horrified. He had hoped to create a more intuitive alternative to Heisenberg's matrix mechanics, but instead he had developed a theory that seemed to deny the existence of definite physical reality altogether. The wave function appeared to be describing a ghostly realm of potentials and possibilities rather than actual particles with definite properties. But the equation worked. It predicted the exact energy levels of hydrogen atoms, explained the periodic table structure, and laid the foundation for understanding chemical bonding. Every calculation that could be done with Heisenberg's matrices could also be done with Schrödinger's waves, and often much more easily. The two approaches were mathematically equivalent, but Schrödinger's version provided a more intuitive framework for thinking about quantum systems. The Schrödinger equation revealed something unprecedented in the history of science, a mathematical law that governs probability itself. Classical physics had been deterministic. If you knew the initial conditions precisely, you could predict the future with perfect accuracy. But quantum mechanics was inherently probabilistic. Even with perfect knowledge of a quantum system's wave function, you could only predict the probabilities of different measurement outcomes. This wasn't just a practical limitation. It appeared to be a fundamental feature of reality. The universe, at its deepest level, operated according to laws of chance, governed by mathematical precision. If you want to understand why quantum mechanics seems so bizarre, you need to grasp the concept of superposition, the idea that quantum systems can exist in multiple states simultaneously until they're observed. It's not that we don't know which state the system is in, it's that the system literally exists in all possible states at once, with different probabilities for each possibility. Imagine flipping a coin, but instead of the coin being either heads or tails while it's spinning through the air, it's somehow both heads and tails simultaneously until it lands and you observe the result. That's essentially what happens with quantum systems. An electron doesn't just have an unknown position before you measure it. It exists in a superposition of being at multiple positions simultaneously, with its wave function describing the probability amplitude for each location. This superposition principle explains some of the most beautiful phenomena in physics. When atoms emit light, they do so because electrons make quantum leaps between different energy levels. But according to quantum mechanics, before the photon is emitted, the atom exists in a superposition of the higher and lower energy states. The emission process involves a coherent superposition that allows the atom to radiate light with precisely defined frequencies. The mathematics of superposition is elegant but mind-bending. If a quantum system can be in state A or state B, then it can also be in any combination of states A and B simultaneously. These combinations aren't just mathematical abstractions, they correspond to physical realities that can be measured and manipulated. Quantum interference effects, where different parts of a wave function cancel each other out or reinforce each other, are direct consequences of superposition. But superposition raises profound questions about the nature of reality. If an electron can be in multiple places at once, why don't we ever observe this directly in our everyday experience? Why does quantum weirdness seem to disappear when we look at objects larger than atoms? The answer involves what physicists call decoherence, the process by which quantum superpositions are destroyed through interaction with the environment. In the microscopic quantum world, particles can maintain their superposition states because they're relatively isolated from external disturbances. But larger objects interact constantly with their surroundings through electromagnetic radiation, air molecules, and countless other influences. These interactions cause the delicate quantum superpositions to collapse almost instantly, leaving behind the definite classical properties we observe in our macroscopic world. The boundary between quantum and classical behavior isn't sharp. It's a gradual transition that depends on the size, temperature, and isolation of the system. Scientists have now demonstrated quantum superposition in increasingly large objects, from individual molecules to tiny mechanical oscillators, but the quantum effects become exponentially more fragile as size increases. By 1935, Schrödinger had grown deeply uncomfortable with the implications of his own equation. Quantum mechanics suggested that microscopic systems existed in superposition until observed, but what happened when quantum effects were amplified to macroscopic scales? To illustrate what he saw as the absurdity of the quantum worldview, Schrödinger devised a thought experiment that would become the most famous paradox in physics, Schrödinger's cat. Imagine, Schrödinger proposed, a sealed box containing a living cat, along with a diabolical device. Inside the box is a Geiger counter monitoring a small sample of radioactive material, so small that there's exactly a 50% chance that one atom will decay within an hour. If the Geiger counter detects a decay, it triggers a hammer that breaks a flask of poison gas, killing the cat. If no decay occurs, the cat remains alive. Here's where quantum mechanics becomes troubling. According to the theory, before anyone opens the box to observe the outcome, the radioactive atom exists in a superposition of decayed and not decayed states. The quantum mechanical wave function describing the entire system, atom plus Geiger counter plus hammer plus poison plus cat, would be a superposition of two possibilities, one in which the atom has decayed and the cat is dead, and another in which the atom hasn't decayed and the cat is alive. The logical conclusion, if you take quantum mechanics seriously, is that the cat itself exists in a superposition of dead and alive states until someone opens the box and observes the result. Only at the moment of observation does the wave function collapse, randomly selecting one outcome or the other based on the probabilities encoded in the quantum state. Schrödinger intended this thought experiment as a reductio ad absurdum, a demonstration that quantum mechanics, when taken to its logical conclusion, led to obviously ridiculous results. Surely cats couldn't be simultaneously dead and alive. There must be something wrong with the quantum mechanical description of reality. But the cat paradox revealed something deeper than Schrödinger intended. It highlighted what physicists now call the measurement problem. At what point does a quantum system stop existing in superposition and take on definite classical properties? Is it when the atom decays? When the Geiger counter clicks? When the poison is released? When the cat dies? Or only when a conscious observer opens the box? Different interpretations of quantum mechanics give different answers to these questions. The Copenhagen interpretation, favoured by Bohr and Heisenberg, suggests that quantum systems remain in superposition until they interact with a classical measurement apparatus. The many-worlds interpretation proposed decades later suggests that all possible outcomes actually occur in parallel universes. Somewhere in the multiverse there's a branch where the cat is alive and another where it's dead. But perhaps the most important lesson of Schrödinger's cat is that it forces us to confront the role of observation in quantum mechanics. The act of measurement doesn't just reveal pre-existing properties, it appears to play a fundamental role in determining what becomes real. This insight would prove crucial for understanding quantum mechanics and would eventually lead to practical technologies like quantum computing and quantum cryptography. The cat remains in its box, simultaneously dead and alive in the public imagination, a perfect symbol of the quantum world's defiance of common sense and its challenge to our understanding of reality itself. Schrödinger had given quantum mechanics its most powerful mathematical tool and its most enduring paradox. His wave equation could predict the behavior of atoms and molecules with unprecedented accuracy. But it also suggested that reality itself was built from probabilities and possibilities rather than definite facts. The man who sought to make quantum mechanics more intuitive had instead revealed just how strange the quantum world truly was. But Schrödinger's discomfort with his own theory was shared by the greatest physicist of the age. Across Europe, Albert Einstein was waging his own war against quantum mechanics, convinced that the theory was incomplete and that a deeper, more sensible description of reality must exist. The stage was set for the greatest scientific debate in history, a philosophical battle that would determine not just the future of physics, but our fundamental understanding of the nature of reality itself. In Brussels, at the most prestigious physics conference ever convened, Einstein and Bohr would clash over the very meaning of quantum mechanics, with the fate of scientific realism hanging in the balance. The outcome of their debate would shape physics for generations to come, but it would also leave us with questions about the nature of reality that we're still grappling with today. Chapter 8. The Great Quantum Debate. It's October 1927, and in a grand hotel in Brussels, 29 of the most brilliant minds in human history are gathered around polished wooden tables, engaged in what would become the most consequential scientific argument ever witnessed. At stake isn't just a theory or an equation, it's our entire understanding of reality itself. On one side sits Albert Einstein, the man who revolutionized our concept of space and time, his wild hair and penetrating gaze reflecting a deep unease with the direction physics is heading. On the other side, Niels Bohr, the Danish physicist whose gentle demeanor masks an iron will and a radical vision of quantum reality that will shake Einstein to his very core. This is the story of the Solvay Conference of 1927, where the future of physics, and perhaps reality itself, was decided through intellectual combat so intense it would echo through the corridors of science for generations to come. The invitation was simple, elegant, and carried the weight of scientific destiny. Ernest Solvay, the Belgian industrialist whose fortune came from an improved method of making sodium carbonate, had a vision: bring together the world's greatest physicists to wrestle with the most perplexing questions of their age. By 1927, that question had become singular and urgent. What does quantum mechanics actually mean? As the autumn leaves fell across Brussels that October, something extraordinary was happening inside the Hôtel des Indes. Never before had such intellectual firepower been concentrated in one room. Einstein was there, of course, along with Max Planck, the reluctant father of quantum theory. Marie Curie, the only woman among them, brought her hard-won authority on radioactivity. Max Born, Werner Heisenberg, Erwin Schrödinger, Wolfgang Pauli, Louis de Broglie, names that would become legendary in the annals of physics, all gathered around those tables with a sense that they were participating in something historic. But this wasn't just a meeting of minds, it was a battleground. For the past 2 years, quantum mechanics had emerged in two seemingly different forms: Heisenberg's matrix mechanics and Schrödinger's wave mechanics. Mathematically, they had been proven equivalent, but their philosophical implications remained deeply troubling. Quantum mechanics worked brilliantly, predicting atomic behavior with unprecedented accuracy. Yet it suggested something profoundly unsettling about the nature of reality itself. The tension in that Brussels hotel was palpable. These weren't just abstract discussions about mathematical formalism. At stake was humanity's understanding of whether the universe operated according to definite, knowable laws, or whether uncertainty and probability were fundamental features of reality. Einstein, who had helped birth quantum theory with his work on the photoelectric effect, was becoming increasingly uncomfortable with where his intellectual child was heading. He would later confess to a colleague that quantum mechanics was so disturbing, he sometimes wondered if he should have become a watchmaker instead of a physicist. The stage was set for a confrontation that would define not just the future of physics, but our entire conception of what it means to exist in this strange quantum universe. As the delegates settled into their discussions, it became clear that Niels Bohr and his collaborators had developed something far more radical than just a new theory. They had crafted an entirely new way of thinking about reality itself. What emerged from their work in Copenhagen wasn't just mathematics, it was a philosophical revolution disguised as physics. The Copenhagen interpretation, as it came to be known, rested on a foundation that would have seemed absurd to any physicist just a generation earlier. According to Bohr and Heisenberg, quantum mechanics doesn't describe what's actually happening in the atomic world, it only describes what we can observe and measure. The wave function, that mathematical entity that Schrödinger had developed to describe quantum systems, wasn't a representation of physical reality. Instead, it was something far stranger, a catalogue of possibilities, each with its own probability of being observed. Think about this for a moment. Imagine you're holding a coin and someone asks you whether it's heads or tails. Common sense tells you that even before you look, the coin is definitely either heads or tails. You just don't know which. The Copenhagen interpretation of quantum mechanics says this common-sense view is fundamentally wrong. According to Bohr, an electron doesn't have a definite position or momentum before you measure it. It exists in what they called a superposition, simultaneously occupying all possible positions with various probabilities until the moment of measurement collapses this ghostly cloud of possibilities into a single, definite reality. But the strangeness doesn't end there. The act of measurement itself plays a crucial role in creating reality. Before measurement, quantum systems exist in a realm of pure potentiality. The moment a conscious observer interacts with the system, the instant a detector clicks or a photographic plate is exposed, the wave function collapses, and one specific outcome crystallizes from the quantum foam of possibilities. Bohr introduced another concept that would become central to quantum thinking: complementarity. He argued that certain properties of quantum objects, like wave and particle nature, are complementary aspects that can never be observed simultaneously. An electron behaves like a wave when you design experiments to detect wave properties, and like a particle when you design experiments to detect particle properties. But it's meaningless to ask what an electron really is when nobody's looking. The very question, according to Bohr, reveals a classical prejudice that has no place in quantum reality. This wasn't just a new scientific theory, it was a direct assault on centuries of scientific thinking. Since Galileo, physics had been based on the assumption that the natural world exists independently of our observations of it. Scientists were like detectives uncovering the hidden truths of an objective reality. The Copenhagen interpretation suggested instead that the boundary between observer and observed was fundamental and unbridgeable. Reality, in some sense, was a collaborative creation between the quantum world and conscious observers. As Bohr laid out these ideas in Brussels, you could almost feel the intellectual ground shifting beneath the delegates' feet. But if Bohr expected easy acceptance, he was mistaken. Across the table, Einstein's eyes were narrowing with the intensity of a man whose deepest convictions were under attack. Einstein's discomfort with the Copenhagen interpretation wasn't just intellectual, it was visceral, almost spiritual. Here was a man who had spent his career revealing the elegant mathematical harmonies underlying physical reality, from the photoelectric effect to special relativity to general relativity. Each of his great discoveries had shown that beneath apparent complexity lay beautiful, deterministic laws. Now his colleagues were telling him that reality itself was fundamentally probabilistic, that God really did play dice with the universe. His rebellion began with a simple but devastating question: is the moon there when nobody looks? This wasn't a flip remark, it was a philosophical probe aimed at the heart of the Copenhagen interpretation. If quantum mechanics was truly fundamental, if measurement really created reality, then what happened to macroscopic objects when nobody was observing them? Did the moon exist in a quantum superposition of positions, somehow smeared across its orbit until someone pointed a telescope in its direction? Einstein's genius lay not just in his theoretical insights, but in his ability to construct thought experiments that exposed the logical implications of theories. Throughout the conference, he presented a series of increasingly sophisticated challenges to quantum mechanics, each designed to show that the theory led to absurd or contradictory conclusions. One of his most famous challenges involved what we now call the EPR paradox, though the full version wouldn't be published until 1935. Einstein imagined two particles that had interacted and then separated by vast distances. According to quantum mechanics, these particles would remain entangled. Measuring one would instantly determine the properties of the other, regardless of the distance separating them. To Einstein, this suggested that quantum mechanics was incomplete. Either information travelled faster than light, violating his theory of relativity, or the particles possessed definite properties all along, hidden from quantum mechanical description. "Spooky action at a distance," Einstein called it, his voice heavy with skepticism. How could nature permit such mysterious correlations? Surely, he argued, there must be hidden variables, unknown properties that determined the behavior of quantum systems in advance, making the apparent randomness merely a reflection of human ignorance rather than fundamental indeterminacy. Einstein's challenges weren't driven by stubbornness or inability to understand the mathematics. He understood quantum mechanics as well as anyone in that room. His rebellion sprang from something deeper, a philosophical conviction that the universe operated according to comprehensible, objective laws. "I cannot believe that God would choose to play dice with the world," he declared, expressing not religious dogma but a deep faith in the rational structure of reality. Night after night in Brussels, Einstein would corner his colleagues in the hotel lobby, presenting new thought experiments, new challenges to quantum orthodoxy. His persistence was legendary. Einstein comes down to breakfast and finds an objection to the uncertainty principle, Heisenberg later recalled. "During the whole day we debate it, and in the evening at dinner we convince ourselves that the objection is not valid. But next morning Einstein has found a new objection." Yet beneath Einstein's intellectual assault lay a profound sadness. This was the man who had helped create quantum theory, whose work on the photoelectric effect had earned him the Nobel Prize. Now he found himself increasingly isolated as the physics community embraced interpretations that violated his deepest convictions about the nature of reality. The revolutionary was becoming a conservative, fighting to preserve a vision of objective reality that his own discoveries had helped to undermine. If Einstein was the master of the thought experiment, Niels Bohr was the master of philosophical subtlety. Where Einstein wielded logic like a sword, cutting straight to what he saw as the contradictions in quantum mechanics, Bohr deployed a more nuanced approach, patiently examining each challenge and revealing the classical assumptions hidden within Einstein's arguments. Bohr's genius lay in his ability to turn Einstein's own insights against him. When Einstein raised the spectre of faster-than-light communication through quantum entanglement, Bohr showed that no information could actually be transmitted this way. The correlations were real, but they couldn't be used to send messages or violate relativity. When Einstein argued that quantum mechanics must be incomplete because it couldn't predict individual outcomes, Bohr replied that this wasn't a flaw, but a feature. Quantum mechanics was complete precisely because it recognized fundamental limits to what could be known. Perhaps Bohr's most profound insight was his concept of complementarity, which he extended far beyond physics into a general principle about the relationship between knowledge and reality. Classical physics, Bohr argued, had been seduced by the dream of a view from nowhere, the idea that scientists could step outside the universe and observe it objectively. Quantum mechanics revealed this dream as an illusion. Every observation required an interaction between observer and observed, and this interaction was always mediated by classical measuring instruments operating according to quantum principles. Consider Bohr's analysis of the double-slit experiment, that cornerstone of quantum weirdness. When you send electrons through two slits without detecting which slit each electron passes through, you observe an interference pattern, proof that each electron somehow passes through both slits simultaneously. But the moment you set up detectors to determine which slit each electron uses, the interference pattern disappears. Einstein saw this as evidence of some mysterious connection between consciousness and quantum reality. Bohr saw it as proof that the classical concept of an independent reality was fundamentally flawed. The key insight was that you couldn't separate the quantum system from the apparatus used to observe it. The electron plus the slits plus the detection screen plus the human experimenter formed an indivisible whole. Try to analyze any part in isolation, and you miss the essential quantum nature of the complete system. This wasn't a limitation of human knowledge. It was a fundamental feature of reality itself. Night after night, as Einstein presented his challenges, Bohr would respond with what colleagues described as an almost inexhaustible patience. He would examine each thought experiment in microscopic detail, often staying up until dawn to work through the implications. And invariably, he would find the subtle flaw in Einstein's reasoning, usually an unconscious assumption about the independence of quantum systems from their means of observation. Bohr's defensive strategy was deeply philosophical. He argued that Einstein's discomfort with quantum mechanics stemmed from an attachment to classical concepts that simply didn't apply at the quantum level. Words like position, momentum, and trajectory were meaningful only in the context of classical physics. Applied to quantum systems, they became what Bohr called complementary, useful but mutually exclusive ways of organizing our experience of quantum phenomena. This complementarity extended to the very language physicists use to describe quantum systems. Bohr insisted that we had no choice but to use classical concepts and classical language, even when describing quantum phenomena that transcended classical categories. This created an inherent limitation in our ability to visualize or intuitively understand quantum mechanics, but it didn't make the theory incomplete, it made it profound. By the end of the conference, Bohr had successfully deflected every one of Einstein's challenges, but more than that, he had articulated a vision of science that was simultaneously more humble and more radical than anything that had come before. Science couldn't reveal ultimate reality, but it could provide increasingly sophisticated ways of organizing and predicting human experience. The quantum world wasn't bizarre because it violated classical expectations. It was beautiful because it revealed the limitations of those expectations. As the Solvay conference drew to a close, something remarkable had happened. Not the victory of one side over another, but the emergence of a new scientific orthodoxy. The younger generation of physicists, Heisenberg, Pauli, Born, Dirac, had witnessed the epic battle between Einstein and Bohr, and they had made their choice. They embraced the Copenhagen interpretation not because it was comfortable, but because it worked. This marked a crucial generational shift in physics. The older generation, represented by Einstein and Planck, had grown up in a world where classical physics seemed to provide a complete description of reality. They had experienced quantum mechanics as a deviation from the natural order, a necessary but disturbing departure from the way the world should work. The younger generation had no such attachment to classical intuitions. For them, quantum mechanics wasn't a deviation from reality. It was reality. Wolfgang Pauli, known for his sharp wit and sharper criticism, captured this generational divide perfectly. When older physicists complained about the conceptual difficulties of quantum mechanics, Pauli would dismiss their concerns with characteristic bluntness. One should no more rack one's brain about the problem of whether something one cannot know anything about exists all the same, than about the ancient question of how many angels are able to sit on the point of a needle. For Pauli and his generation, the question wasn't whether quantum mechanics made sense according to classical standards, but whether it made accurate predictions about experimental results. This pragmatic attitude became the dominant ethos of quantum physics. Most physicists adopted what became known as the shut up and calculate approach, attributed, probably apocryphally, to Richard Feynman. Rather than wrestling with the philosophical implications of quantum mechanics, they focused on applying its mathematical machinery to solve problems and make predictions, and the machinery worked with spectacular success. Max Born, one of the architects of quantum mechanics, later reflected on this period with a mixture of pride and unease. "I'm now convinced that theoretical physics is actually philosophy," he wrote. "It has revolutionized fundamental concepts, for example, about space and time, relativity, about causality, quantum theory, and about substance and matter, atomistics. And it has taught us new methods of thinking, complementarity, which are applicable far beyond physics." Yet even as the quantum establishment consolidated its victory, the philosophical questions raised by Einstein didn't disappear. They went underground, surfacing occasionally in the work of maverick physicists who refused to accept that the interpretation of quantum mechanics was a settled question. David Bohm would later develop a hidden variable theory that reproduced all the predictions of quantum mechanics while maintaining Einstein's vision of objective reality. Hugh Everett would propose the many worlds interpretation, suggesting that all possible quantum outcomes actually occur in parallel universes. And decades later, John Stuart Bell would prove mathematically that Einstein's vision of local realism was incompatible with the predictions of quantum mechanics, vindicating Bohr's position in a way that even Einstein couldn't dispute. But in 1927, as the delegates packed their bags and prepared to return to their home institutions, the immediate future of physics was clear. Quantum mechanics would be taught, developed, and applied according to the Copenhagen interpretation. A generation of students would learn to think quantum mechanically from the beginning, without the conceptual baggage that had made the theory so troubling to its founders. The quantum establishment had won not through force of argument alone, but through the simple fact that their approach worked. While Einstein continued to search for a more complete theory, his former colleagues were using quantum mechanics to understand atomic structure, chemical bonding, stellar nucleosynthesis, and the properties of matter under extreme conditions. The theory that had emerged from the crisis of the early 20th century was becoming the foundation for the physics of the future. As we leave that historic hotel in Brussels, with its polished floors still echoing with the footsteps of giants, we might pause to consider what had really been decided in those intense October days. On one level, the Solvay Conference had resolved a technical dispute about the interpretation of a mathematical theory. But on a deeper level, it had redefined humanity's relationship with the natural world. For 3 centuries, from Newton to Maxwell, physics had been animated by the dream of complete knowledge, the idea that with sufficient information and computational power, the future of the universe could be predicted with perfect accuracy. The Copenhagen interpretation didn't just abandon this dream, it declared it impossible in principle. Uncertainty wasn't a reflection of human ignorance, but a fundamental feature of reality itself. Einstein left Brussels unconvinced, and he would spend the remaining 30 years of his life searching for a theory that could restore his vision of objective reality. He never found it, but his search wasn't futile, because it forced physicists to think more deeply about what quantum mechanics actually meant. Every challenge Einstein raised, every thought experiment he constructed, every argument he marshalled against quantum orthodoxy contributed to our understanding of this strange new reality we found ourselves inhabiting. The great quantum debate of 1927 wasn't really settled until 1982, when Alain Aspect's experiments finally tested the predictions that had emerged from that Brussels hotel room. But that's a story for another chapter. For now, it's enough to recognize that in those few days in October, the course of human understanding took a sharp turn toward the mysterious, the beautiful, and the utterly unexpected. The classical world of definite objects with definite properties had given way to something far stranger. A quantum reality where possibilities dance with probabilities, where observation creates reality, and where the deepest questions about the nature of existence remain as fascinating and elusive as ever. The quantum establishment had won the battle, but the war between classical intuition and quantum reality would continue to rage in the hearts and minds of physicists for generations to come. And in that ongoing struggle between what we expect reality to be and what quantum mechanics tells us it actually is, we find one of the most profound and beautiful intellectual adventures in human history.